with this computer, and we might as well, oops, close this, don't need that anymore. Okay. Okay, so today we'll talk about exterior walls and from the beginning. So let me just make sure I can annotate. Okay. Okay, now you can appreciate that what happens with exterior walls is that here you've got, of course, you have the axial load that's, if it's a bearing wall, okay, you have the axial load that's being supported by the bearing wall, and at the same time you do have the wind that pushes on the wall, and therefore you still have what we call a combined loading. Okay, so the stud wall selection tables provides combination of the factored compressive strength PR and the maximum factored lateral resistance WR that satisfies the interaction equation. Now, we talked about this last week. Okay, if you remember, when you have, okay, I'll do this. Okay, so if this is my stud wall, okay, and okay, so I have a load coming down here. If it's a bearing, like normally, if this is an exterior wall, what happens is that you have your trusses, okay, that are supported by that wall. So therefore, you have all the loads that are coming down from the roof, plus you have the loads that are in the wall, the wall itself. So that's going to be your gravity loads, your vertical loads, and that's going to be this here, your PF over your PR. And then at the same time, you're going to have some kind of wind that is going to be blowing onto the wall. And therefore, the wind, what they do in this table, instead of working with MF and MR, what they do is they want you to calculate what the WF would be caused by the wind. In other words, just calculate this. And then what they will do in the table, they will give you a resisting WR. Okay, so all you have to do is compare if the resisting WR on this side is greater than the WF on that side, then you're okay. And the way that the tables work, I'll explain it when we get to the tables, but that's what you're basically doing, okay? So in the tables, this gets replaced by a distributed load, a WF acting by the wind and a WR that the stud can actually provide in order to counteract the wind. And I like the way they did it because it simplifies the way to choose a stud to satisfy your design conditions. Now, okay, values and tables are only valid for the conditions outlined in the checklist. So like I said, I love this handbook because this handbook kind of, asks you a number of things before you go straight to the tables and you take your values. And this is the checklist. So the checklist says, okay, to verify that the tabulated resistance given in the stud selection table, okay, are appropriate for the structure being designed, the following questions should be asked, okay? Is the load duration short-term? Now, short-term for the combined loading conditions. In other words, the answer is yes, because the short-term load they're talking about here is the wind, and wind, of course, is a very short-term load. In other words, 2 to 3 seconds at most. Okay, it's less than 7 days, no problem. Now, are the surface conditions dry? So normally, you would use this table to design the studs of your exterior walls that are going to be supporting everything, the roof and everything, and therefore, of course, you know that you're going to be inside of an envelope of the building. In other words, it's all going to be protected, so the answer is going to be yes. Is the material free of incisions and fire retardants? You're not going to be using any kind of treated wood, so the answer is yes. Are the studs effectively plined and laterally strained at both ends? Okay, so by putting a plate here, and by putting the plates up here, okay, and making sure that the plates are well connected to the trusses and that this is well connected to your foundation, you can safely assume that it's going to be pin connected, okay? So you can say yes to that. and and prevented about buckling about the weak axis. So normally when you're designing an exterior wall, you're always going to be putting some kind of a sheeting, and normally you can either put an OSB board, which is a cheap way of doing it, or you can put plywood, okay? And therefore the answer would be yes. And since you are nailing the plywood with the same conditions that you did for the floor, okay, does the stud wall meet the requirements of a case 2 system? In other words, case 2 system, if you remember, are there at least 3 members, generally parallel together? So when you have a wall, you will have at least 3 members. Are the members not spaced more than 610 millimeters apart? And normally you will start spacing your studs maximum at 610, in other words, 24 inches. And then after that, and then is there a sheeting material of at least, what is it, 9.5 millimeters thick? And normally the sheeting material that we put on the outside of the wall is always a 1/2 inch thick plywood. And the answer would be yes. So therefore, because what's going to happen is that when they calculated the resistance of the stud, they assumed that the plywood was going to contribute to the resistance of the stud, just like on the floor. So in this case, for an exterior wall, you could say yes. And when you say yes, you just have to make sure that in your specifications, you tell whoever's going to be building your structure what are the nailing requirements that they're going to have to provide. Okay. And normally what you do, if you're doing a lot of wood structures, you'll have a typical what I call detail sheet, and on that detail sheet you'll basically show, you know, like a plywood, and you'll show the like, and then you'll show like along the edges you want the nails to be at every 150 millimeters, and in the intermediate, and you'll have a typical detail telling the carpenter, and you're going to specify a minimum of 2-inch nails. You understand? So this is what they normally do. So the carpenter will probably use 3.5 inches and so on. So, and therefore the answer would be yes. Now, is the stud eccentrically loaded less than 1/6 of the, okay, now I will talk about this later on, okay? I won't talk about this right now. And I will explain to you what they mean by 1/6 of the depth of the stud, okay? And I'll explain this to you. I don't know if you guys do any eccentric loading in your soils class, where you have like a non-uniform load distribution underneath your footings. Do you guys do that at all?
No, we never did actually. We only
Okay,
did.
uniform.
Yeah, exactly.
Okay, so I'm going to explain this, okay? I'll explain this so that you guys, you don't have to panic. This is very simple to understand if it's explained easily, okay? So I'll talk about this later on. So I won't talk about this now. And of course, in our case, if this is our top plate, right? Like usually you put 2 plates when it's a bearing wall on top and 1 plate at the bottom. That's a typical way of okay. And of course, if your truss is coming right across here, you can consider it to be concentrically loaded. So you don't have a problem there. In other words, you can consider that you meet uh, you okay, yes, the answer would be yes to this case, okay? Now, so that's the checklist. And like I said, the handbook is great for that. It gives you like a reminder of, can I use the tables, yes or no? Okay, and if it's no, then you have to do something, either modify the value in the table, or, and when it comes to compression members, you have to do everything from scratch. In other words, you would have to use this equation here, okay? So that's the only choice you have after that. Now, if you guys are interested, we can do one, but now, here's the wall selection table, okay? I think I only gave you one. Okay, so I'm going to expand it so you guys can see it a little bit better. Okay, now uh, is it clear to everybody what we're looking at? Okay, now
Yes.
the only thing I don't like about this table, quite frankly, I'll tell you right now, okay, they start at a length of 3 meters, which is pretty stupid because most exterior walls start at 2.44 meters. So they could have gone from 2 to 3 instead of what they did here, start at 3 and go all the way to 7. I mean, I've never seen 7-foot walls, 7-meter walls, you understand? So I find that whoever developed this table wasn't a practitioner. He was an idiot. So, but excuse the expression, okay? So as far as I'm concerned, so in other words, when you're designing a wall for 2.4 meters, if it's good for 3 meters, it will definitely be good for 2.44 meters. So therefore, you would be looking at this length here, okay? Okay, and then instead of like jumping by a meter, they could have done it like anyways. Like I said, they could have been more practical. They could have done anything from 2.5 meters to, and anyways, like I'm just saying. So what they've done here, okay, first of all, this is the species, so SPF, and of course this is the grade. And this is normally what you would find when for the studs for building your exterior walls. In other words, we're going to be using SPF #3 stud grade. Like I said, if you buy the handbook, you're going to have all the grades and all the species. You're going to have a series of tables in the hand grade, okay? Now, what they've done here, okay, I don't know if you can appreciate this, okay? Of course, this is for a 2x4, 2x6, and very rarely do you see a #3 stud grade for a 2x8. So I don't even know why they've included this in the table. Very hard to find. Most likely that this would be a #1, #2 grade. So if they did all these calculations based on a #3 stud grade and you happen to use 38x84 #1, #2, your value would only be that much stronger. So don't worry about it. Now that's #1. Okay, so these are the most common ones that we use to build walls, 2x4s or 2x6s. Okay, now the reason why we tend to use 2x6 is because we want to be able to create the cavity. Okay, so this is my 2x6. Okay, we want to be able to create the cavity so that we can put enough insulation so that we can have the right R value for our exterior wall. And that's why we use 2x6s. It doesn't mean it's not, the 2x6 is done more so that we can create the cavity of where the insulation is going to go in. In other words, we're going to fill this up with insulation in here. And that's why we use 2x6s. So the thing about using 2x6s, what's nice about it is that if they're too strong, well, you space them out further apart, you understand? And then you go up to 24 inches. And if they're still too strong, you don't care. They're going to be ample for your structure. So so the 2x6 is now, you might get into some architects, they might want to put more insulation on the wall. In other words, they want to create a bigger cavity and they're going to tell you use a 2x8 and therefore you would be using this table here. It's the architect that's going to tell you how much of a cavity he wants you to create in your structure so that he can insulate and get the right R factor for his exterior walls, okay? Because he has to obey the energy law that's in force, and he has to make sure that the R value of his wall meets that R value dictated by the law of conservation of energy. Okay, now so that's #1. #2, okay, here the maximum PR, okay, PR prime and WR prime. Okay, so in other words, what they did here, which is smart, okay, you'll notice that if the PR prime is small, the WR prime is big. Okay, so and if you look at the equation, PF over PR plus MF, I'll put it over MR and all that. Okay, so you can appreciate that if this ratio is small, then this ratio can be big. So what they did here is they said, well, let's fix this. If this happens to be a PR of 1, I can go up to this side of a WR of 7.7. So what they're doing is that as the PR gets bigger and bigger and bigger, of course, in other words, as this ratio gets bigger and bigger and bigger, this one has to get smaller and smaller and smaller. So what they've done is they've kind of worked out a series of values where the value of PR here, your PF over PR, and your WF or your WR, so that when you take the two of them, you'll always get less than or equal to 1.0. And that's what they're doing in this table here, okay? And I'll show you how to use this table. It's not that complicated. Now, here, of course, in our case, if we're looking at the trusses going right over the wall, our eccentricity is 0. So therefore, we will be looking for the WR in this column here, okay? This is where we were looking for the WR. And here is if your eccentricity is up to D over 6. Now, guys, just so I'm going to try to explain this right now. You don't have to, I'm doing this more for your general information, okay? And I don't expect anybody to, you're not going to get tested on this or anything, but it's good to know, okay? First of all, okay, what's eccentricity, okay? Okay, in other words, what happens is that if I have an axial force, okay, P, okay, and it doesn't coincide with the centroid, okay, then if this is E here, okay, therefore P times E, a force times a distance, what does that give me? What's what's the what's the what's the result when I take a force and I multiply it by a distance?
Moment.
Exactly. So in other words, this will create a moment. Okay, so this will create an additional moment that you have to compensate for in your member. So if you want to calculate E, you take your moment and you divide it by your force, and that gives you the E. So for example, if your moment is 100 kilonewtons, okay, meter, and your force is 1000 kilonewtons, therefore your eccentricity is 0.1 meters or 100 millimeters. Okay, so what they're saying here is that if you happen to have a stud wall, okay, and if your E is greater than D over 6, in other words, D over 6, this is D, okay, and it divided by 6, because this is what they call the middle third. Okay, so in other words, if I have M divided by my P, and this is MF divided by PF, okay? If this value is greater than in other words, if, like what's 140 divided by 6? Does anybody have a calculator very close at hand? Somebody very quickly. 140 divided by 6. I get 23.3 millimeters, okay? So if this eccentricity here exceeds 23.3 millimeters, then you cannot use this table. Okay, you have to use the equation. That's all. Now, what happens is that you'll hear this term somewhere if you guys continue and you'll either hear it in your courses if you continue in engineering. Okay, you'll hear that if the resultant falls within the middle third, and the D over 6 is what they mean by the middle third, when this is the maximum eccentricity, so that if I look at my foundation, okay, and if the resultant falls within the middle third, the tension here will be 0, and it will be like this. This is the way that the pressure distribution is, okay? Now, so this only happens when E, okay, is less than or equal to D over 6, or in this case, if this was like your foundation B, E should be less than B over 6. So this is what they mean by middle. When it happens to go over D over 6, this is what happens, okay? This is what I'm going to try to draw it. I'm going to draw it right over, okay? I'm going to change color so you guys can see this. When it happens to go over D over 6, well, you don't have this anymore where you have the maximum compression and then the tension goes to 0. This is what happened. On this side, it goes into tension. So therefore, you have this type. So here you've got tension happening on this side. And therefore, the whole analysis becomes different here because this part, the soil cannot take any tension, and therefore you have to now resolve your forces and so on and so on. And that's what happens also in the stud, is that if the eccentricity happens to be greater than D over 6, so instead of having inside here your compression force that looks like this, okay, you end up getting both compression and tension inside your stud, and you can't use these values anymore. So that's what they mean by the eccentricity being less than D over 6. So, and you'll hear the term, the resultant falls within the middle third. What they mean is that it falls within the middle third. In other words, this is the middle third here, and the result. So for example, this is where the resultant is, right here, of a triangle, and it falls within the middle third. In other words, the third, like, you know, for a triangle, the middle third of your triangle. And that's what they mean by following the middle third. So this is just for your general information, okay? If you guys want, I can, you know, if you guys are really interested, I can get more and more into this, but that's just so you can understand what they mean by why this restriction is, because up to this point here, everything will be, so in other words, when it's less than D over 6, this is what happens. When it's less than D over 6, you have compression, you have compression, you have compression. You understand? When your eccentricity is 0, well, then you have a uniform right across, you see? And the greater the eccentricity, the more that this is like goes to 0. And if it exceeds D over 6, then you start getting compression and tension. And that's where you have to worry about, because you know that this is it doesn't work anymore. So you're starting to get really high values on this side. So that's what that is. And like I said, in our case, we don't have to worry about it because we will be worrying about our eccentricity equal to 0. But if you want to use the tables, and if you happen to go over d over 6, like I said, E is simply your moment divided by your force. So it's mf over pf. That's all it is, okay? And that's how you calculate the E. And if that value happens to be greater than whatever these numbers divided by 6, then you can't use the tables. You gotta go use the formulas. That's all they're saying, okay? So that's the restriction here. Now, the other thing I like about this table, I'll talk about it right now, okay, is that at the bottoms of the table, okay, you have some good values, okay? You have, for example, you have the QR value for and these are the same as in the other stud tables, 20.6, 30.2, and okay, so you have your QR value. They also give you the VR value, which is very good because you'll have to check for the shear of your stud. So for a 2x4, yeah. And at the same time, they give you the stiffness of a number 3 stud, of a 2x4, a 2x6, and a 2x8. So these three values are going to be also good because you will have to check for bearing, you will have to check for shear, you will have to check for deflection, and therefore this is where you come and check if everything is okay. Okay. And that's it. So you see, so what they're doing basically here, they're kind of showing you here the PF, the E, and the length and all that, okay? And they're making sure that the E falls within this here maximum. And what I like about this table is that you calculate your WF, and what the table gives you a WR, and then depending on the PR and the PF ratio, then you can go see if the WR is, and so on. And I'll show you how. I'll apply this to an example. It's not very hard. And of course, guys, very important, okay? Make sure your slenderness never exceeds, okay? Make sure your slenderness never exceeds. As a matter of fact, if I'm not mistaken, okay, I'm just gonna do this. If I'm not mistaken, okay, the reason why you get no more values here is because the slenderness exceeded 50, okay? That's why you have no more values here. So whenever you're looking at a table that gives you values for compression and you don't see any more values, that's because you've exceeded that slenderness ratio. It's cuts, okay? So we'll come back, we'll use this table in an example, okay? And you're gonna have to use this table for your project, so you're gonna get familiar with it. And of course, you're gonna have to use this table for the exam, so on and so on, but that's secondary for me, okay? So when a load is not applied at the centroid of the vertical axis of a compression member, it is eccentrically loaded, and that's what I just finished explaining, okay? The additional moment created by eccentricity should be taken into account when designing the compression member. Now, the value is tabulated for loads applied concentrically on this table, and you see, so in other words, where E is 0 and up to a maximum of E, where E divided by D is, D divided by 6, 1/6 of the depth of the stud, you can still use the table, okay? If it happened to be greater than that, well, you use the formula. Use PF over PR squared plus MF over MR squared times that whole thing. Just use that equation, and that's how you do it. So instead of the tables, you'll have to use the equations. That's it. Do not use the values in the tables when the eccentricity exceeds 1/6 the depth of the stud. And of course, it tells you that you can go up to D over 6 for your eccentricity. Now, here, well, now let's do a design problem and see how we're going to use the tables to solve our problem, okay? And this is what I like about exterior walls, okay? It's going to bring in load combination number 3 and load combination number 4. So this way you'll see how those two get applied in the design of a structure. I'm sorry, I was taking a sip of water. So here we go. Okay, now stud spacing 600. Like I said, guys, typically we start our spacing of our stud at 600. And the reason why we start at 600 is because if all of a sudden, first of all, if it doesn't work at 600, then we have the option of going down to 400. And then if it doesn't work at 400, we have the option of going down to 300. So we start at the furnace. And why don't we go over 600? Because if we want to take advantage of a case 2 system and therefore getting more resistance because we have a load sharing system and so on, you should not go over. I've seen idiots in my colleagues spacing things at 32 inches, which was, I think it's 8 something. I said, why'd you do that? You lose all the benefit of the case 1 and case 2. I said, what was your big bonus for doing that? That's why it worked out. Idiots. Okay. Anyways, now I'm using 3 meters because the table has a 3 meter. Okay, that's the only reason. Like I said, in your project, you have a length of 2.44 meters. Well, if it works for 3, it's definitely going to work for 2.44. So don't worry about that. Now, the specified vertical dead load is 2.2 kPa. It's not too bad. Not too bad. And the vertical snow load is 4 kPa. Okay. Now, and then I will show you how, like from your ADA, how you get these values. It's not very hard, okay? Now, the tributary width of the roof truss is 5 meters, okay? The tributary width of the roof truss, that means that the truss has a 10-meter span. Everybody understands? In other words, I'm only taking what is tributary to the wall. So in this case here, the span of the truss would probably be 10 meters. I'm taking half the span of that truss, which is acting on my exterior wall. So basically what's happening here is this, okay? I have an exterior wall here. I have an exterior wall here, okay? And I have my truss going like this. Okay, I should have drawn a little bit better. And half, I should have drawn a little bit better. Half is going to that side, half is going to that side. So most likely this is a 10-meter span, and therefore 5 meters is going there. And now my snow load that's coming down here is 2.4 kPa. I'm sorry, my snow load is, and then the dead load of the roof is 2.4 kPa, okay? Which is pretty high. I mean, I find compared to the snow load, but it doesn't matter. It's just an example. So now the specified wind pressure, 0.883. Okay, so that's for strength. Now, there's a difference between, and when we do the lab, I'll remind you why, okay? It's all because of the importance factor that for strength, this is the value of the strength, but then for serviceability, you reduce it. You only take 75% of this value, and that's based on the importance factor, okay? And if you take this, multiply by 0.75, that's why you get this value here, okay? And you'll understand it when we do the lab. So now we have, of course, we have dry service conditions because it's going to be a wall, and we have untreated slumber because we don't need to treat it. It's going to stay in a relatively good environment. Studs effectively pinned, okay, by the roof truss and the foundations, okay, and are concentrically loaded. That means the truss goes right over the top plate, and therefore you can consider it to be concentrically loaded. And the buckling is prevented by the weak axis where the wall sheeting are fastened and meeting the class 2. So that means I'm giving you all the situation that, like this, we're going to have sheeting, it's going to be nailed properly, the weak axis is going to be laterally supported, blah, blah, blah. And I'm doing this basically why? So that when we're solving our problem, when we go here, okay, and we look at our checklist, is the load duration short term? Yes, it's a wind. Is the service condition dry? Yes. Okay. Is the material free of incision? Yes. Are the pins effectively? Yes. Does it? Yes. You understand? Yes. Okay. So we're saying yes, so we can go straight to the tables. That's why I did it that way. And when you're designing a wall for a house and the studs go, and like I said, whatever you're be supporting, as long as it goes over the whole width of the plate to transfer the load, you can consider it to be concentrically loaded. So the answer would be yes. So now, of course, this is what I like, okay? Now here, there's no longer load combination 1, load combination 2. Because we're talking about wind and snow, we're talking about load combination 3, 1.5 times your dead load, 1.5 times your snow load, and you take only 40% of your wind load. In other words, these are your companion loads, and this is your principal load, okay? And then, so here I take 1.25 times 2, 1.5 times 4, I get 8.5 kPa. So this is the axial load, okay? In other words, right now, for case number 3, I have a PF equal to 8.5, but this is case number 3, okay? And now my WF, so in other words, here's my wall, okay? Here's my wall. I have a PF of 8.5, and I have a WF acting on the wall. Okay, and that's what I like about doing it this way. It's very simple, okay? And of course, PF is equal to the factor load, sorry, this is the factor load times the tributary area. And of course, the tributary area is the tributary width times the stud spacing. So therefore, I get a PF value of this is my tributary area. I hope everybody can appreciate this. Your studs are every 6 meters, 0.6 meters. The width is tributary. So therefore, one tributary width multiplied by the other tributary width gives you a tributary area. And we end up with 25.5 kPa. So here, so my PF right now is 25.5 kPa. That's the axial force. And now I will calculate my WF. So this is your wind load multiplied by your stud spacing. Because you want to get a WS, you only have to multiply by a tributary width in this case. And therefore we end up 0.2 kilonewtons per meter. So here I have a WF of 0.2 kilonewtons per meter. Okay, so basically, so this is what you have to keep in mind. So when you go into the table, you're going to look for a PR value that is greater than your PF value. And then right beside it, you're going to check to see if your WR value is greater than your WF value. And if it is, you satisfied both conditions. So that's what we're going to be doing. And that's just for case number 3. And then we'll have to do the same thing for case number 4. So here, the load combination case number 4. Now what happens is that the companion load becomes a snow load, okay? And of course, the way you see it written, and this is what I find so stupid, they put 1.25 D, okay, plus 1.4 times W and 0.5 snow, which is really stupid the way they do it, because this is acting this way and these are acting these way. So this has to be added to this, and this is in the other direction. So this is the way you should really be looking at case number 4. Because this is a gravity load, this is a gravity load, this is a lateral load. You cannot add a lateral load to a gravity load, okay? And the way they show it to you, I find that unless you don't, especially for students who, have a hard time seeing vectors and directions, I find it's very misleading. It's almost like saying, take your gravity load and add your wind load to it. It makes no sense. Your gravity load goes this way, your wind load goes that way. So they're two separate animals. You can't add a vertical load to a horizontal load. Totally impossible, okay? And they will both have different effects on your member. So I find that's really stupid that whoever came up with writing that in the, anyways, like I said, I should get onto these committees and, tell the guy, show that, add the gravity loads to the gravity loads and show that the principal load, that the load factor is 1.4 and no longer 0.4. Anyways, so I hope you appreciate what I'm saying to you now, okay? So therefore now, of course, my factor load will reduce because I'm only taking half the snow load here, okay? So therefore it went down, but my wind load will go up. So in other words, my axial force goes down, but my bending moment goes up because I'm no longer 0.4, I'm at 1.4 here. And WF all of a sudden goes up to 1.66 kPa. Now, it's the same tributary areas, same tributary width. The only difference is that the values change. So therefore, it's the same tributary area, okay, as before. And it's 0.3 meters. So now I went from 25 to 13.5 for my PF, but my WF went up, okay, substantially. It went from 0.2 to 0.7 kilonewtons. So now I've got the two things that I need to satisfy. I need to satisfy the PF and then check the WR for case number 3, the PF and the WRs for case number 4. And they both have to be satisfied in order for me to make sure that the stud can meet the total requirement required by the different load combinations. So now I'll show you what we need to do, okay? So basically, from the stud selection table, select the size that satisfies the strength interaction from case 3 that is concentrically loaded, okay? So what that means is that we go here, okay? We come here, and we know that we have a length of 3 meters. We have, basically, we have like, for example, even if I can't even use a 2x4 because I can go up to only 8.3. But here, for example, I know that if I have a PR of 27, okay? In other words, if I have a PR of 27, I will end up with a WR of 0.27. And I know that in my case, okay, my PF is 25 and my WF is 0.2. So I know that this and this is greater than what I need for case number 3, okay? So that's for case number 3. And then when I go to case number 2, I look for a PR that's at least 13.5. And then I just check to see that the WR is greater than the WF for case number 2. And if that's the case, then this will meet both combination number 3 and combination number 4. So, and guys, you are not allowed taking this PF here and taking that WR. If you choose this PR, you got to choose, you have no choice, but in other words, there's none of this, okay? In other words, once I choose this as my PR, this becomes my WR. Not that, not that, not that. In other words, you have to be consistent, okay? So for example, I could have even gone to, for example, I knew that for case combination number 2, I had 0.7. Now I could have even taken this. 16.9 is greater than my PF value and my WR is still good. So I know that in that case, it's still okay. So that's how I use the table. I check for case number 3, make sure I'm okay for case number 3, and then I go back and check for combination number 4, make sure I'm okay for combination number 4. And that's what I'm doing here. So basically for combination number 3, if I take a 38 by 140 stud, I have a PR value of 27, great, which is greater than my 25.5. Now I go right across to the column next to it and I get a WR value of 0.27, which is greater than my 0.2. That means that my moment will be totally satisfied for combination number 3. Is anybody lost? Now's the time to ask me.
I think we're okay, sir.
Sorry, it's quite clear.
Yeah.
Okay,
That's good, sir.
as long as it's clear. Hold on a second. Forgot to mute my phone in case somebody calls. Okay, so it's clear, I'm happy. Now, like I said, what you did, is that once I picked this PR from the table, I had no choice but to use this WR prime for the moment. So that's what I want you to really understand. You don't, go one PR there and one WR up the table. You got to read right across, and those are all the values you get. Now, check for combination number 4. Okay, so we had 13. So here, this is 13.5 is equal. So that's okay. And then my WR value was 0.977. So therefore, case number 4 is okay. So that means that since the PR and the WR for case 3 and the PR and the WR for case number 4 are both satisfied, then this stud would be strong enough to satisfy the requirements of the load combinations. Is that okay with everybody? Now, once you've checked for strength, then we have to do a few other things, okay? Now, we have to check the shear, okay? Now, the shear basically, if you remember, okay? If you remember the shear, let me take this, okay? So here's my stud, okay? And basically, okay. Okay, so I have a wind load. Now, which WF do I use? Of course, I use the higher of the two. I use the WF from load combination number 4, because that's the one that gives me the highest one. I use the WF from load combination number 4. And how do I calculate the shear force here? Well, it's simply equal to WF L over 2, just like a beam, okay? And that's what this is, okay? So what's WF from case number 4? L is the length of your stud, and that's how simple it is to calculate the shear. So therefore 0.7 from load case number 4, because it's the higher of the two, okay? And L, of course, is the length of your stud, and therefore my WF is 1.05 kilonewtons. Now, like I said, when you go to, what I like about the stud selection tables, if you go to the bottom, we're using 2x6s, so therefore it tells me right away the VR value here for a 2x6 is 10.8 kilonewtons, okay? And that's where I get the value. So as long as my VF is less than 10.8, I'm okay. So I get 10.8, so I'm okay. So I've got strength for bending and for axial forces combined. It's okay. And I've got the shear, it's okay. What's the last thing we have to check for?
Deflection.
Sorry?
Deflection.
Deflection, exactly. Okay, serviceability. Let's call it serviceability, and therefore in this case we have to check for deflection. Now, we know that 99.9% of the time when they build an exterior wall, there's going to be gypsum on the inside face of that wall. So therefore, since there's gypsum, what's recommended is that you limit the deflection to L over 360. So that's something you should know, okay? What should be the deflection? L over 360, because most likely they're going to be putting gypsum. So check deflection, wall finish susceptible is cracking, okay? And of course, W is equal to L over 360. That's your deflection criteria when something's susceptible to cracking. And this is the equation to calculate the deflection of a member that is simply supported with a uniformly distributed load right across the whole member. And here I put WW. In other words, I put the service load for wind, okay? And okay. So and then I put everything in terms of ESI, the stiffness of my stud. ESI is the stiffness of the stud, and therefore I put, okay, almost the same thing that we did for the beams, okay? So here now I use 0.265 because that is the load that we use for serviceability. In other words, we take 75% of the wind load for serviceability, and then I multiply by the tributary width to get my specified wind load, which ends up being 3.75. Okay, now if you don't do this and it's still okay, well, you got no problem. In other words, if you would use the 8.33 instead of this, no problem. And if it still works, not a problem. But this is the, if you want to be sure that you don't run into an issue, this is what you're supposed to be doing. Now, I calculate the ESI required, and of course, always bring it to the scientific notation 10 to the 9th, because that's how you're going to find the values in the table, okay? And in my case, I ended up with 47.5 times 10 to the 9th Newton millimeter squared, the same units that we had for the joist, for the beams, everything else, okay? And the same scientific notation. Now, of course, like I go back, and like I said, this table is really good because it does give me the stiffness. Sorry, I wanted to draw instead of, it does give me the stiffness here. So I have times 10 to the 9th, I have 78.2. 78.2, and therefore 78.2 is greater than 45, and therefore you can see that this deflection would be way less than L over 360, so it's way stiff enough. And I believe you got to check bearing, of course, all the time. Now, the bearing QR has to be greater than QF. And if you remember, what is bearing? Bearing is the axial force that is perpendicular to the grain. Okay, so this is your bottom. Here's your top plates, and here's your bottom plates like this. Okay, and therefore, what you want to make sure of is that the QF here, in other words, the force that is perpendicular to the grain, okay, the QF is less than or equal to your QR value, okay? And that's what you want to make sure of. And of course, in this case, what is the biggest force perpendicular to grain? That comes from load combination number 3. So therefore, and that, of course, 25.5, load combination number 3. So for shear, you see it comes from combination number 4. For bearing, it comes from number 3. And of course, I should have gone to the table, but if you go to the table, I should have put another hyperlink here. And you also find that value, okay? You have the QR value here of 32.4, okay? So you get the bearing resistance, you get the shear resistance, and you get the stiffness all at the bottom of this table, which is very nice. I mean, you don't have to do any calculation. And of course, if you buy the book, they'll have the QR, the VR, and the ESI for all the species and all the grades. And the only thing that you will not see a change in when it comes to the species, for every species, these values are always exactly the same, because the bearing resistance does not vary with the grade. It only varies with the species. And if I'm not mistaken, that's it. So guys, you should do assignment number 5 for next week. It's going to be a typical question that you can have in the exam. So at least you start getting familiar with it. And this way you can see where you're, because I can tell you guys, I can do 18 examples, and until you start doing your own example or your own assignment, you will never know where your, let's call it, the hurdles are that you have to overcome or you haven't grasped. And that's why we, the best thing to do is work on
Can I
this.
ask you a question about the assignment?
Yes, go ahead.
Okay, because there is the sketch and then the sketch of the, I don't know how to say, I don't know how to use a proper term, but like the, it's like a cut. So it says that there's the lengthen and the build-up column, and then it says that it's a 3,000 and then 3,000 on the other side. But then it says that the studs are spacing like 600 millimeters. So I don't really understand that sketch, like what this 3,000 is referring to.
You mean cross section?
Yeah, the
No,
cross section.
okay, okay, hold on. I know exactly what you're talking about, okay? Okay, first of all, I'm going to stop sharing this. And I'm going to share with you my whiteboard, okay? So Rena, the reason why I gave you that sketch, okay, is because in theory, the next assignment is going to be a continuation, and that's what you're going to see, the same sketch on the next assignment, okay?
Oh, okay.
And I'll explain to you what it is, okay? And then when we're going to be doing the project, you'll understand totally, okay? Because in an exterior wall, okay, of a house, okay, in an exterior wall of a house, fair enough, we have studs, right?
Yeah.
So if we only had studs, not a problem. We design a stud and our design is complete. You agree?
Yeah.
Okay. But what happens is that if I have 4 walls and I put studs all around, what's going to happen?
I don't know.
You won't be able to get into the house.
Oh, okay.
You agree?
Yeah.
So what you need to do is you need to make openings for doors, right? Now, if you make only an opening for a door, you can get into the house, but then you won't be able to see outside, right? So what do you need to do? You need to make windows. You follow?
Yeah.
So what this is that, so in general, your stud wall, okay, I'm saying your stud wall is spaced at, the spacing is at 600, because like I said, that is you start with a spacing of 600. Now, so you design the stud wall, and normally your stud wall should end up being a 2x6, okay? Do you understand what I'm saying? Okay.
Yeah.
Then once you decide that your stud wall is going to be made out of a 2x6, okay, then what's going to happen is that you're going to have to start designing the lintels that have to support all your roof trusses to make the openings for your windows.
Oh, okay.
And therefore you'll be able to design the lintel. And then when you need, and then these things have to be sitting on built up columns. So therefore you know what size of lumber to use for your built up columns. And then what's going to happen is that these built up columns are going to be subjected to an axial force from the lintel. And guess what else they're going to be subjected to? A bending force from the wind. Okay. And this is, this is exactly where I love, so therefore we're going to have to design this column for load combination number 3, load combination number 4. Okay. And that's why that sketch is going to be a continuation of next week's lecture. And the assignment is going to be design the lintels and design the built up columns.
Okay.
You understand? Okay, so like, I could have waited to give you all the assignment in one shot, design the wall, because that doesn't take very long, you understand? Now that you know what to do, okay? But then after that, I figured I might as well break it up and let you do one piece 1 week and do the other piece the week after.
Okay. Do you
Okay.
know when we're gonna have the second test?
Right after we finish the built-up columns and lintels. So we can have it right after week number 10. We can have it, okay?
Okay.
So in other words, once we learn how to design the lintels are going to be simple. You're just going to have to realize how the load gets applied. The lintels are built-up beams. It's something that you've already done. You understand? What's going to be a little bit more complicated are the built-up columns, and they're not really complicated because we've already done some. You understand? But next week I'll reinforce the whole built-up column with the eccentric, you know, with the, and we'll go through that. Okay.
Not next week, because next week we have
The week
Monday
after.
special on a Thursday, right?
No, what I'm saying, next week we're going to learn how to design the lintels and the built-up columns, and then the week after we'll have the exam.
Yeah, but like not next week because we don't.
Well, what I mean, Rena, when I talk about next week, I'm talking about next lecture. Okay.
Okay. Yes. Okay.
So like, see, this is why whenever we're talking, okay, I don't talk into, like, for example, calendar weeks. I say week 10.
Yeah.
You see, so week 10, I know that week 10 is not next week because next Thursday is you still have, so next week you're gonna have to put up with me twice. Is that okay, Rena?
We put up with you twice. Anyway.
I know. So I know that. That's why I was just joking. So do you understand what that sketch is all about? It's a continuation of the design of an exterior wall where you have openings in the walls. Okay, is that clear now?
Yes, thank you so much.
You're welcome. But for now, like, just design the exterior walls. And like I said, Rena, we normally use 2x6s because we want to create the cavity. Okay. And we normally start at the spacing at 600 or 610 if you're doing an imperial because it's 24 inches. Okay, so good question. I'm glad you asked, and that's why it's a little confusing. But now you can appreciate why we have windows, right? And we have doors.
So, sir, I
Yes.
thought the windows so the people from the outside see the inside.
Oh, is that what
I'm disappointed.
so that's what you do when you walk on the streets? I'm sorry, Omar. You're like, my wife loves looking inside windows. I don't even bother. Understand? I always thought windows were meant so that you can look outside to see if you have to put on some shoes or not because it's snowing out there. You know? That's what windows are for, you know? And to let in some daylight. Well, windows, Omar, if you want to know, what's the primary purpose of a window?
To let the sun in, I think.
No.
The light, the sun. I don't know.
It's the light, and what else?
Fresh air.
Exactly, ventilation. Okay, so there's a certain ratio of your area of your floor that you have to have for your window for the light, and then there's a certain ratio that has to be operable for your ventilation. Okay, that's all in the building code. So if ever you want to know what size window should be, it's all specified in the building code to let in enough light and enough fresh air. Understand? Unless you have a mechanical ventilation system in your house, then you don't have to worry about the ventilation. Okay, so that's it for, okay, so now what we'll do is I can close this, stop sharing. I will close the, and now we'll talk about the project. I love talking about the project. I hope I'm not, yeah, okay, so now you guys are gonna see what you would actually have to do if you were designing a house, because, you know, contrary to book examples where they give you the load, they give you this, they give you that, you're going to have to calculate all your loads, and I'm going to walk you through it step by step, okay? Step by step, so that you guys, you know, okay, oops, where am I? Okay, so what time is it? We finish at, okay, so guys, what we'll do is we'll do this lab, and I think it should take about a maximum an hour, okay? That means we'll finish at 5, And then from 5 to 5:30, I'm pretty sure a lot of you might have a lot of questions regarding your truss. Or do you have no questions regarding your truss from last?
Yeah.
You
Yeah,
have.
sure.
I have a question.
Oh, yeah, we do.
Exactly. So let's go through this, okay? And then what I'll do is we can talk. We'll spend the up. I mean 5:30, guys. I don't care if we're here until 7. Well, wait, not 7. My wife's gonna kill me. But I don't care if we go past 5:30. So it's up to you guys, okay? I don't want to overburden you, but I'm here to give you as much help as I can while I can. Okay, so guys, exterior now. Sorry.
I leave at around 4:30, so I just want to let you know, so you don't think of me being rude. Just leaving the session, but I will leave around 4:30.
I'm sorry, you didn't come in very clearly, and it must be me that. Can you repeat what you just said?
Oh, I just wanted to let you know that I will have to leave around 4:30. I have an appointment, but like I just wanted to let you know to not be rude and to just.
Okay, well, thank you for letting me know. So if if you have any questions regarding, just keep them till the next lab. Okay, sounds good. I hope you guys are talking amongst yourself and you're helping each other out and you're discussing this, because that is a nice thing to do. I mean, some of you can work perfectly well by yourselves, but don't feel like, all I don't want to see is, if I see that people are copying exactly the same mistake as the other guy, I know one guy copied off the other guy, you guys are going to get 0. I want you guys to work together and collaborate and check answers and discuss who's right and who's wrong and so on and so on. Okay, so here we go, slideshow from the beginning. Okay, now you have, this is our project. Like, now, don't forget, I'm continuing my project now. Like, it's not like I have no information at the tip of my fingers. I've done my truss analysis, and believe it or not, from my truss analysis, I can get all my vertical loads for my exterior wall. Okay, and I'll show you how to do that if you need to do that. Okay, now, first of all, let's look at the geometry of our wall so that we get an understanding. Okay, so what we're going to be doing is that our wall is going to be 2.44 meters high. We're going to space them at every 6 meters, at every 2 feet. Okay, this will end up being the tributary width of one stud when we're looking at the wind load. Okay, we're also going to be the tributary width of the stud when we're looking at the load caused by the dead load and so on. Okay, so this is what you're actually seeing. So we're going to start with spacing our studs at every 2 feet, and of course we know that it's 2.4 meters high, and therefore the tributary area of each stud is going to be 1.44 square meters. And you'll see where this becomes important is when you're calculating your wind load. Okay, so that was just to give you an idea. I want everybody to see it. And of course, like, we are going to have windows and we're going to have lintels and all that, but let's just worry about doing the studs now, and then we'll move on to where the openings are. So we first worry about the general structure of the wall, and then we worry about those isolated situations that we have to design for in order to take care of our loads. So that's our geometry. I hope everybody sees this. Okay, I mean, this is clear to me. I mean, I know that you say, yeah, you've been doing it for 40 years, of course. And so that's our geometry. Now, specify dead load from the roof truss. So in other words, what we're actually doing, is, okay, we have our truss here. Okay, and we have our exterior walls. Okay, and here's our exterior wall. Okay, and of course it's going to be sitting on the floor. Okay, so what we need to, why can I not go and find the forces that are coming into the exterior wall? Okay, how do I do that? Well, I've analyzed my truss, so therefore the reactions of my truss will give me the forces that are going to be going into my stud. So the Ry here on this side and the Ry on that side will give me my PF or my P. I shouldn't even use PF. I'm going to use P. In other words, I would use the specified force, and that's where, and I said, why don't I just go and get those values from ADA? Okay. So basically what I did was I said, okay, from the truss analysis, I looked at the resultants of just the, the dead and the superimposed dead. And don't forget that our trusses were spaced at every 0.6 meters, which coincides with the spacing of our stud. So therefore, we're looking at the same tributary width. And I went to ADA and I got me 1.55 kilonewtons as being the dead load. And that included the weight of the truss, all the dead load, the superimposed dead load that we put on the roof members, and all the superimposed dead load that we put on the bottom cord, okay? Now, all I did there is I had a load combination. I called it, okay, dead load. I put 1.0 D, okay, and then I put 1.0 SID, okay, and I ran the analysis and I went to get the reactions, and that would be the dead load from the roof, okay, and that's how simple that was for me, okay. And I did the same thing, of course. I went to get this SLS, the serviceability limit states. In other words, we take the snow load of equal to 0.1, and I go look at the reaction of the truss under the snow load, and it gave me 7.03 kilonewtons, okay? Now, if you want, I mean, if you want to take your time and, that this is your truss, okay? This is your truss here, okay? And you know that here, this is 1.5, this was what, 1.5 feet, this was 1.5 feet, and this was 27.75 feet, and convert this all into meters, take that. We had a snow load here of I think it was 1 point something, and if you do it, you're gonna get exactly the same value. So it's up to you. But I said, I've already done all the work. The computer program is gonna give me the value, and there's my snow load. Now don't forget, this is 100% snow load. So this is good for load combination number 3. When I'm going to be doing load combination number 4, I will take half this value. That's all it is, okay? So that's how that's how I take advantage of ADA to simplify my life, because it gives me numbers. It does the analysis for me and gives me my results right away. So clear all the drawings, and so now the specified. Now, of course, the exterior wall also carries. It carries the plywood, the insulation, this and that, and the sheeting on the inside, blah, blah, blah. That is dead load. So if you want to account for that, okay, so what you do, this is exactly the same values that we used when we were calculating the perimeter footing. I don't think I've changed any of these values, okay. I use the same thing, the exterior cladding, I use the plywood, I use the, whatchamacallit, the self-weight of the stud, and then the insulation, the gypsum board, and so I rounded up to 0.4 just in case that, I don't care. So now so this is what the wall weighs, okay? So in other words, it weighs, what's this, about 0.5, anyways, and I like to look at it in terms of pounds per square foot. Now, how do I convert this into a load that the stud has to carry? Well, the same thing. I multiply by the tributary width, multiply by the tributary height, and therefore I can convert this into a force. So therefore I take the 40 kPa, multiply the spacing is 0.6 meters, the height is 2.4. So each stud in theory is carrying 0.56 kilonewtons of dead load. Now what I do is I take this dead load, of course, and I add it to that dead load, and that will give me the total dead load on the stud. So the total dead load right now, 1.55 that I got from ADA plus 0.56 ends up 2.13 kilonewtons, which isn't bad. Remember that problem we had? We said that the dead load was, oh no, that was in kPa. That was pretty high. So there we go. So that's going to be my dead load, and that's going to be my snow load, okay? Now all I got to do, of course, is put these values in and just multiply by the load factors. I don't have to worry about tributary width, tributary heights, tributary this, tributary areas. I've already got them in terms of a force. And that's, that's already going to give me my PF value right away just by multiplying this by 1.25, multiplying this by 1.5. I get my PF for case number 3. 1.25, 0.5, I get my PF for case number 4. And that's how easy it is once you. So, like I keep telling you guys, the analysis, the more you understand the analysis, the more information you can take from it. And of course, you do it very accurately from the very beginning so that all the values are going to be later on used for whatever reason, you know that you can rely on them, and you don't, and of course, you should always double check to make sure everything's okay. As a matter of fact, what I did when I looked at the, when I looked at this here, okay, I made sure that I did a quick calculation based on and I ended up, I think I ended up getting 7.025 something, and it rounded up to 7.03. That's what so I know that ADA did not make a mistake, and I did not make a mistake when I inputted into the ADA. Okay, so there it goes. There's my snow load, and there's my dead loads. Okay, now I'm sorry. Now, what's going to be a little bit longer here, okay, is calculating your wind load. Okay, so the wind load is like anything else. Okay, here's a formula. You've seen this formula before. Okay, so the wind load is equal to the importance factor times the reference velocity times the exposure factor times the gust factor times the external pressure factor. Okay, so these are all, and you've seen this before. So therefore, you're going to just have to go and be patient and find the value. So the external pressure acting statically, okay, so that's the pressure, and the importance factor and the reference velocity based on a probability of 1 in 50 years, or once every 50 years, or 1 in 50 years, I should say. The exposure factor, CE, the gust factor, and of course, the external pressure coefficient. So there's your equation. Now, what happens here is that when you're talking about cladding, okay, when you're talking about a wall, you have both external and you have internal pressures, okay? So therefore you have to calculate the external one and the internal one, okay? And of course, if this is the windward side, in other words, if this is the wind direction, on the other side, you have the internal one and you have the external one. So therefore you have to calculate it for both sides and see which one gives you the worst scenario. So now, so the net specified pressure due to wind acting on all surfaces of a building shall be the algebraic difference. And that's where they make the difference, because one's going to be positive, the other one's going to be negative, but the vectors are acting in the same direction. So they're going to give it, you have to basically sum them up. And that's where they talked about the algebraic difference, because like I said, I shouldn't have erased that sketch, because here's my stud, okay? So what happens is that the wind load is here, okay? So it's going to, this is a positive value, and this is going away from the surface. This is a negative value. So therefore, when I take the algebraic difference, I take this minus this. I literally have to add that to that. And that's what they call the algebraic difference, because you're really adding them together because they're both acting in the same direction. So that's what the algebraic difference means. Now, this is the internal one. Like the internal one is the same formula, except what changes is these two, the internal gust factor and the internal pressure coefficient. Okay, that's what changes, but everything else stays the same. So now, so this is, of course, I means internal pressure. Okay, and the importance factor stays the same. The reference value stays the same. The exposure factor stays the same. The only thing that changes is the internal gust factor and the internal pressure coefficient. And don't worry, I will give you these values, because these values come right out of the supplement to the National Building Code, and that's where I got them, and I will provide those for you, okay? Now, of course, if you remember, there are 4 categories of buildings: low, which I never consider in my design. To me, this is completely BS, okay? In other words, I don't believe that a farmer's life is less important than anybody else, because usually farms like barns and stuff are built as low. So I don't like this. Normal means, you know, all buildings except those, okay? And of course, high. So as far as I'm concerned, even though there's a low, I never use these values. I've always considered either normal, high, or post-disaster, okay? And if my client says, well, it's a low building, I says, well, find another engineer. I'm not designing it. And like I said, now what I like you to notice is here, okay? You'll notice that, and that's why, like here, they're saying that you can reduce all your loads by 20% when it comes to strength. Well, I won't reduce my loads by 20%. I will use 1, okay? Now, what I want you to notice is the serviceability, okay? And that's where the value changes, you know, from strength to serviceability. You only take 3/4 of your specified load for serviceability, as opposed to what you do for strength. And that's what you have to keep in mind. And that's where that comes from, right here, okay? And that's the same, the serviceability, no matter what category, it's always the same value. Of course, the importance, and these are the same, okay? Like for example, this is the same for snow as it is for wind. So keep that in mind, okay? Now, of course, our house is a normal, so therefore we're going to be taking a value of 1.0 for the strength, and we're going to be using 0.75 for the serviceability, just to make sure of that. Now, we know that. Now, where do we find the value of Q? Well, the same place we find everything else in terms of, we go to Appendix C of the National Building Code, right? And of course, in Appendix C, we will have all the provinces across Quebec, across Canada. And of course, then it starts from British Columbia going all the way to Newfoundland. And then you have all the cities also in alphabetical order. And in our case, we are in Montreal. So it basically makes no difference where we are in Montreal. They're all about the same. So we are here, okay? And we're looking for, I should have gone just a little bit further, okay? And we're looking for the probability of 1 in 50. And therefore we have, this becomes our Q value for Montreal, okay? And like I said, what's nice about this is that you see that up here, up in northern Quebec, this is one of those Inuit places, you know, like look how strong the wind is up there. Look at this one, 83.83. Good place to go fly a kite. What do you think? Look at that, 0.9. Okay, so it's really windy up there. Okay, that's what I like about this table. It tells me where to go and where not to go. You understand? Okay, so I'll clear that. So that's where I get my Q value. Okay, now the exposure factor. Now, are you in an open terrain or are you in a rough terrain? That's the only thing you have to worry about. Now, if you're in an open terrain, this is the formula to calculate the exposure factor. And of course, like I never worried about being in a rough terrain. I've always taken to be in an open terrain. If it happened to be in a rough terrain, I'm only that much safer. So I always use this formula here anyways. And this is the idea, what they mean by, like, if you build your house out here somewhere where there's very little trees and it's very open, then you should consider using this value. Okay, that's open terrain. And then of course, for you to be considered rough terrain means that the terrain is suburban or urban and wooded terrain extending upwind of the building uninterrupted for at least 1 kilometer. Wow. So I got to make sure this house is 1 kilometer upwind. In other words, upwind can be in any direction. So I have to, within a 1 kilometer radius, I have to have houses all around me, or 10 times the building height, whichever is the greater. Okay, so if my building happens to be a meter high, I have to make sure that within 10 kilometers that the everything is considered to be a rough terrain. So, and of course, this is the equation. It lowers the CE value. Okay, now, and of course, the reference height above grade is the H value, and then this means that from 0 to 12 meters, you have a minimum height of C value 0.7, that's all. And of course, so here what they're trying to show you is all these houses here would have to be designed for open terrain. This house here, if the distance from here to here, and the distance from there to there, and the distance from there to there, and the distance from there to there happens to be at least 1 kilometer, then this little house here you can consider to be rough terrain. So all these houses here would have to be open terrain, and then these houses, if you want, you can design them for. And does it really make that much of a difference? I don't think so. But anyways, it's there. Sometimes I think they try to do things to, it really doesn't justify what they're doing, but it does. I mean, terrain, winds will slow down if the terrain is rough. That's for sure. Okay. Now, this was our geometry. So the reason why we need our geometry is because when we're looking at wind loads, okay, the wind load, the coefficients that we're looking for, okay, they come from a different table when you're looking at cladding. It's not the same ones that you saw in structural analysis, okay? Because structural analysis was for the primary frame of the building. That's what you did the wind loads for. So here I have a tributary, each stud will be carrying a tributary area of 1.44 meters. And the reason why I need to know that, you'll see this on the next page, okay? So this is where I want you to understand where the 1.44 comes from, and I'll tell you why we need to calculate that. Okay, you'll see that on the next page, okay? This is what you had last year in structural analysis. You had figure I7. I7 is for the primary structure of the building. In other words, when you're designing the bracing. And we'll use I7 when it comes to our steel building, because we will be designing the, you know, the bracing for it. So, but for the wood, we'll assume that the cladding of the plywood will be sufficient to take care of the lateral loads. So here what happens is that the way that, so here they're telling you, this is where you get your CPCG values, but this is for external peak composite pressure gust factors, okay, on individual walls designed for structural components and cladding. And don't forget, a wall is considered the cladding, okay? So even when you're designing, for example, you want to see the siding here, and if whoever is designing the siding to see that it won't break, this is the table you come to, or this is the graph you come to be able to determine what is the CPCG value that you're going to use to calculate the stresses or the forces on your cladding. Now, you see that this is the area that the member is supporting, okay? So that's what's important. So in other words, and that's why it was important to understand where, you know, what is the area that you can see, the bigger the area, okay, the bigger the area that the member supports, you'll notice like the values diminish. And that's because there's a bigger area that's being distributed over that member, and therefore it diminishes, okay, up to a certain point. So the reason why we need to clear. Okay, so basically what I did here is I simply went here and I said, okay, here's my 1.6. I'm sorry, 1.4. What was the area? 1.44 square meters. It was about here. Okay, you don't have to be precise on this, guys. Remember. So this is the area. This is where the stud happens to fall. Okay, the tributary area of one stud. Okay, and then from here I go get both the positive values are the ones that are on the windward side, and the negative values are the ones that are on the leeward side. Okay, if you remember, the ones that create pressure, the ones that create suction. Okay, and this is just for external. Okay, so therefore I went to get the value here. I think I got a value of about 1.7 or something. You can also use 1.75. And here I think I use a value of about 2. Okay, 2.0 for the suction side. So this is where I came to get the values of CPCG, the windward side and the suction side. So how this table works is very simple. So for example, like if this was, I had a column there, a column there, a column there, a column there, and these are all exterior column. Well, I calculate the area that each column would have to support, take that area, okay, and then come to the table. For example, if that area was 5 meters, I would draw a line here at 5 meters, and then I'd be able to go and read the different values. So it's the area, the tributary area that the member is to resist. That's how this table works. That's what they mean here, area. Okay. Now, so from here, like I said, I think I took one. I'm not sure. I think I took 1.7 here, and here I took a value of 2.0 for the CPCG values. Okay, for the cladding. And please remember that, because I might have made a mistake. So that's okay. So that's where that comes from. Okay. Now, windward side. So you can appreciate we have to first calculate the one on the windward side, then the one on the leeward side. So the windward side, I take the formula. Okay. And this, guys, is something you're going to have to copy in your notes, okay, because I want to see these calculations in your notes. So you better have this in your notes. So you take P is equal to IWQ CE CPCG. Like, I'll know where you got the values from, because I know I gave them to you straight from the lab. And therefore, I get Q. Of course, we have 0.48 kPa. Now, I calculate the value of CE. Since the building does not exceed 6 meters, I know that the CE value is 0.9 right away. Okay, so this is up to from 0 to 6 meters in height. The value of C is always 0.9, so I use that right away. Now, from the table, I got CPCG is 1.7 on the windward side. So this, and therefore, you do the calculation. Will somebody tell me what the value is? Because I haven't done the calculation. Anyway, you do the calculation and you put it in here, okay? Now, on the leeward side, you do the same thing. The only thing that's going to different, this is going to be the same, that's going to be the same, this is going to be the same. The only thing that's going to change is the CPCG value. So therefore, I do it 1.0, 0.4, 0.9, and of course minus 0.2, and that means it's a suction is blowing away from the surface, and there goes my value of P on this on the suction side, on the leeward side of the building. So I'm going to leave this here for so you guys can take time to copy it properly, or you can just take a snapshot, or this thing's being recorded, so whatever way you want to do it, take a screenshot, copy it. All I'm saying is that I want to see these calculations in your design brief, because this, okay. So like I said, so what we've calculated so far is just the external pressures. Now we got to go calculate the internal pressures. Okay, so the internal pressures, well, on the windward side, okay, this is the equation. Now, these I'm going to give you because, like I said, these come straight out of the supplement to the National Building Code, which you guys, I'm not going to spend, you guys spend $180 to go buy that, okay? Now, the importance factor stays the same. The Q value stays the same. The CE value stays the same. The CGI value changes, okay? Now, I don't want to get into too much detail, but this is the value that they recommend. If you're going to have openings, and of course, we're going to have windows. If they have openings, this is the value that they recommend for the CGI. And this is the value, the internal pressure coefficient they recommend for the windward side. In other words, minus 0.45 when you have openings in your thing. Okay, there are different values, but for a house, for a building, okay, if the building has no windows, if it has no openings, it has only one little door, these values change a bit. Okay, so this is what they recommend, because what they're saying is that sometimes you can leave the window open, or the wind can gust right in. That's why they want you to use a gust factor of 2 here, and so on and so on. And now you take these values, you calculate the internal pressure on the windward side. And then on the leeward side, you do the same thing, except that these values will, this stays the same, but this value changes slightly. And of course, this will become a positive value because it's pushing on the wall. Like, what I want you guys to see is this, okay? I want you to see this more than just do it mechanically. If this is my building, right? So this is my building. And if wind is blowing this way, okay, so as the wind blows through the building, okay, you can appreciate that as the wind's blowing through the building, it wants to suck the air away from this wall, and it wants to push on this wall. It wants to suck the air away from this wall, and it wants to push on this wall. So this here is what we calculate on the other page. This here is what we're calculating here, and that's why we have a negative sign, because it's blowing away from the wall. This here, you'll see after. Let me go on, okay? It's got a positive value, okay, of 0.3, and therefore it's pushing on the wall, and then this one is negative, so that's why, okay? These values change from a positive to a negative, because it's just the dynamics of the wind. The wind's blowing through the building, it wants to suck the wind away from the surface, and it wants to push onto the surface, it wants to suck it away from the surface, and that's how wind will actually act on the surfaces of a building. So you guys are going to do the calculation, and you're going to end up getting, okay, the value, okay. And then what you do is, of course, you sum them up, okay. So you sum up here what you got on the, you know, for on the external and the internal one, the internal and the external one. And of course, you take the algebraic difference, means that you take this minus this, you end up with a positive value that's going this way. You take this minus this, you'll get a negative value, and that's why it's a suction. Okay, so that's all it is. So you just keep in mind, because they're acting in the same direction, therefore they do not reduce each other, they just amplify. They keep on adding together. And so that's what you're gonna have to do. So once you have that, well, you're gonna have your pressures. Okay, then you multiply them by your tributary width, which is 0.6, and you're gonna get it, and then of course you multiply it by, okay, whatever load factors, and you can get your WF for case number 3 and case number 4. So hold on a second, let me clear the drawing. So now, of course, the load combination, like I said, this is so stupid the way they show it here. Okay, it almost looks like you add the wind and the dead loads together, which doesn't make sense. And of course, you take half the snow load, and here you take the dead load and the snow load. So these are the two that we're going to be doing. Okay, but like I said, this is so stupid. It's just because here they're using principal loads. Okay, They shouldn't have put a plus sign here. That's what I'm saying. They should have just put 1.4W, not a plus sign. They make it look like you have to add these together. It doesn't make sense. You do not add a vertical load to a horizontal load, okay? You just look at the effects that those two have, and then that's how you have to add them together. Okay, so there you go. Clear all the drawings. Now, case number 3, you take 1.25 your dead load, and then of course this here. So what is W? Well, you know that you just calculated it, right? And therefore you multiplied whatever you calculated in the previous play, multiplied by your tributary width to get your W, and you multiply by 0.4, and that will give you WF, and then you can go through the tables. And don't forget, we got this from the first page, we got this from the first page, and then for case number 4, here you simply take half that snow load from the first page. Here you still take the same snow load, and here the wind load, your WF that you have is 1.4 of your wind load, okay? And then that's it. And then you go to the tables and you check PF for a PR value, WF for a WR, WF value, and you see if and you just check to make sure that we're going to be using 38 by 140 because we need to create the cavity. You just want to check to make sure that they're adequate to carry the forces required by load combination number 3 and load combination number 4.
So can you go back to the slide before it? Just one slide.
Which one? This one?
No, yeah, this one. All right, all good. Thank you.
You understand? All I'm showing you here, who's asking me the question?
Omar.
Omar, all I'm showing you here is that this and this basically add together. This and this basically add together, okay? And you take the higher of the two.
Okay.
You don't do it for this wall and this wall. If the sum of these two is higher than these two, what do you care if it's in suction or in pressure? It's the force is what dictates, you understand? So I did not do the calculation here purposely because this is this is part of your homework or part of your project, you understand? Okay.
Yeah, almost done. Yeah.
Sir, I don't understand. Could you go back just a little bit?
Okay, so why don't you stop me at the slide where you don't understand? That's what I don't understand, but go ahead.
Sorry, no, it's just I was having trouble understanding like the image. Like I understand the windward side and the leeward side. Like I get that in a way.
Which image are you talking about?
The next slide.
The
Like
previous, or when you say this one? Or
no, after, sorry.
Okay. Well, do you understand what we're doing here?
Yeah, we're calculating the side the wind is pushing.
Well, this is external.
This is
no, we're calculating the external one, and this is the one that's where the wind is. The windward side is where the wind is pushing.
Okay.
And then here we're calculating the external one, only the external ones where the wind is a suction.
Sir, I have a question for here.
Yes.
Okay. CP and CG, are they both 1.7 or do I add it in the equation like that?
What do you mean? Well, it's like if you go back here, it says that this table here gives you both the CP, CG together combined as one value.
Okay, perfect.
Okay. So here the external composite pressure gust coefficient, CPCG, okay, pressure gust coefficient. In other words, what's nice about this table is that it gives you both the CP and the CG value combined. Okay, and that's why in this case, whatever you get from here, you've already got the value of these two factors in your equation. Okay. Now, so in other words, this is the external ones, okay, and this is the okay. So in other words, if you're looking at your building like here, like this in plan view, okay, here's okay. So if this is your wind direction, okay, so this one is this one, and the suction here is this one, and that's why you have a negative sign. So it tells you that so this value is this one. Then when you're looking at the internal ones, you're going to get one here, and you're going to get one here. This one's going to be negative, and this one's going to be positive. And that's why you do the algebraic difference. You do the algebraic difference, and then this ends up being positive, and this ends up being negative. In other words, this is blowing away, and this is blowing away. And you take the higher of the two to design your stud. Because you don't care if your stud is being bent this way, or if your stud is being bent this way, it's being bent, and it's the highest bending that's going to govern the stud. It's not in which direction is it bending. I don't know if you guys can see that, but that's what this is, okay?
Yeah, I understand.
Okay. And like I said, guys, it's and this is what you actually have to do when you're, you know, like you take your wind equations and you calculate your wind forces, and you can see that now it becomes a little bit more. It becomes a little bit more involved, because you're not just, because the reason why we didn't do it last year, because you did figure number 7. Look what happens last year. Okay. Here's I'll do it in plan view. Okay. The reason why you don't do it for the primary structure, I'll tell you why. Okay. Or would anybody know why we don't do it for the primary structure?
I mean, first of all, can you explain what primary structure means?
In other words, like where like whatever you're using, like in other words, this is your primary structure, and I want to calculate the lateral bracing system for this structure. The stud in my wall is not a primary structure. It's a secondary structure. You understand? It's not. It's like it's just one member in an overall system. You follow?
Okay, yeah.
So the primary structure means that I'm looking at the structure as a whole, and the wind is acting on the building as a whole, not just on one little member here. Okay. Do you understand what I mean by primary structure now?
Yeah, I got it. So you look at it as a whole structure, and yeah,
exactly. Now I'm looking at a whole structure. So for example, in plan view, like when we're going to be doing the steel, okay, when we're going to be doing the steel, this is in plan view, okay, we're going to be doing the wind loads. Well, we're going to be using the same figure that we use for structural analysis. Why? Because now we're going to be designing the system for the primary structure. In other words, you know, how the building is going to hold together. And the reason why we don't worry about the internal ones here, okay, because when you look in the primary structure, this one goes this way and this one goes this way. These are equal. So in terms of lateral loads, what do these two do to each other? If this is 5 going this way and this is 5 going this way, what's going to be the net effect on the structure?
0. Well, from the inside.
Zero. And therefore, when I'm going to be designing my structure, I'm only going to be worrying this and this. I won't be worrying about the internal ones. You see? Because in this case, they cancel each other out. That's why on the primary structure, we don't worry about the internal pressures. But when you're looking at just this wall here, well, this is going to be there and that's going to be there. So therefore, it becomes, you combine them. And that's why on the primary structure, you don't worry about the internal ones, because they cancel each other out. Because when I'm summing all the forces in one direction, this one will cancel this one. You follow? I'm just telling you this for your general information. Why is it on the primary structure we don't worry about the internal pressures? Because when you sum up the pressures in one direction, they cancel each other out. Okay, and there you go. So now you got all the information, and just like we have done in the lecture, you know, now you can go and calculate your WF, you can calculate your PF, and then you can go for case number 3, case number 4, and then you're going to go check to see if your PR and your WR for a 2x6 is okay for case number 3, for a load combination number 3. If it's okay for a load combination 4, of course, then you've designed the studs for the exterior walls. Or you've confirmed that a 2x6 at every 24 inches would be sufficient to support the gravity loads and the wind loads. Yes, go ahead.
So, just a quick question before Jan. So we do exactly what we did in class today. We go case number 3 and case number 4.
Isn't that how I sum up here?
Yeah.
You do case number 3. You have the value here. The only difference is that this is already in kilonewtons. You understand? This is already in kilonewtons. Do you have to do anything else?
No.
No. The only thing you have to do is get this here. This is right now is in kilopascals. How do you convert it to kilonewtons per meter? You have to multiply by the tributary width. Right?
Yeah.
There you go. And you know, and that you're gonna get like the W. This is gonna give you your W here. I don't know if you guys can see this, but this is your W here. This is your W here. And you take the higher of the two. So whatever these two are and whatever these two are, you take the higher and that becomes your W. My spacing is 0.6 meters. Therefore, my WF becomes, you understand? Whatever value I have here multiplied by 0.6.
Sir, what happens if both of them are the same?
Then it makes then it's perfect. That means either you can take either one to do your design.
Okay.
What I'm trying to make you understand here is that I'm designing this stud here on the leeward side, and I'm designing this stud here on the windward side, okay? Because don't forget, if this happens to be bigger on the leeward side, then what's going to happen is that means that this stud is going to have a higher bending moment due to suction here, right? On this side. That's what it's telling me. What happens when the wind's blowing this way? Shouldn't the stud on this wall be the same strength as on that wall? Because then the force are just going to be reversed. I don't know if I'm confusing everybody by saying that. Now, the wind's blowing this way. Does the wind only blow in one direction on the house?
No.
No.
Okay, so what happens when the wind blows this way? That means all these values go on this side and all these values go on this side. So what strength should the stud be designed for?
Both?
The higher one. If this gives me 1.5 and this gives me 1.2, why should I design for both? When this one, if I design for 1.5, the 1.2 is automatically going to be designed for.
Well, yeah, that's what I meant. Like take both into account, like the higher one, basically.
What I'm saying is that you have to just worry about which one is the highest one, because if you design for the highest one, the one that's lower, you don't have to worry about it. You follow? And on top of that, what you're actually doing is that you're designing for the studs that are along the edges. That's where the wind pressure is the highest. So you're designing for these values. Here they're lower. Are you going to go redesign them for those? No, because if you know they're good for here, they're going to be good for there in plan view. You understand? So, I mean, you know, I leave these blank, and it's almost as if you guys draw a blank in your mind. You understand? I want you guys to do the calculation. I want you to decide which is going to be the higher one of the two, and which ones you're going to be using in your calculations. I mean, I'm showing you what you have to do and how the steps you have to go through. And, you know, if there's something you don't understand, I'll go back and explain it. But, you know, like, tell me now what it is that you don't understand about the wind loads. No, we did all of this. Like in the problem we did in class, we said that the wind load was 0.833 kPa. Well, how the hell they come up with that value? I just showed you how they come up with that value. And then for serviceability, the wind load is 0.6 whatever 25 kPa. Well, you take 75% of that value, that's how you get it for serviceability. And don't forget, when you're doing your design check, you have to check for strength, you have to check for shear, and you have to check for deflection, just like we did in the assignment in your project. And so how did they come up with these values? Well, I just showed you step by step how they came up with those values. So in an example, they just throw them at you, but in real life, you have to calculate your W. And that's how you do it. You calculate all the wind pressures on the external one, you calculate all the internal pressures on the internal one, you check which side has the highest one, and you design the stud for that. And that's how it's actually done. So,
sir, I don't
sir,
think I understand what the internal pressures are. I understand what the external are, but
okay,
like I don't know what the internal are. Like, isn't the building like fully enclosed?
Okay, what happens is this. Okay, no, the buildings. This is it. Okay, what you have to remember. Okay, and I've seen walls collapse. Who asked me the question? Was it you, Alex?
It's Alex. Yeah.
Okay, Alex. Okay. I've seen walls collapse because of the internal wind loads, because they weren't anchored at the top. You know, masonry walls. Okay.
Yeah, that I understand because there's an air gap.
Well, not an air gap. Look, because what you have to appreciate is this: This is I'm doing a plan view like this, okay? This is my plan view. Here's my plan view. Now, I'm going to change color. Here's a window, Alex. Okay? A window. Fair enough? There's a window.
Yeah.
It's summertime. I open the window. The wind is blowing in this direction. Okay? My window is open. So what's going to happen? The wind's going to blow on the stud here. As the wind goes through the house, it's going to pull the air away from this wall, and there's a suction on the internal one, and then it's going to be pushing on this wall here, and then as the wind goes around the building, it's going to be pulling away from the building. So there's your external one. You see how it happens?
All right, perfect. I understand now. That's very clear. Okay.
Okay, and that's what you have to realize is that, you know, you're right. Like if you leave all your doors and your windows closed and you never open up a window, the internal pressures are very little. But can it happen on a windy day? All of a sudden you open up the window, right? You open up the window and you get this gust of wind that comes in here and pulls the wind away from this wall, pushes on this wall. And then as the wind, the external ones are going around your building, they're pushing on the outside, pulling on the outside. And that's what it is, Alex, you understand? And that's what these values that I gave you here about 0.3 and 0.45, okay? Like there are different ones in the supplement, depending on how close the building is. You know,
Okay, got it.
Like for example, like I don't know if you've ever seen refrigerated warehouses. I don't know if you've ever seen those things, but like it's mostly all refrigeration, okay? And therefore they have very little openings. And you should see, I forgot what the values are, but they're very small for the internal pressures because there's very little openings. And then you got the ones where, for example, you have these loading docks. You know, you have these industrial buildings. You know, like, and you have these big loading docks, and you have these big overhang doors. You understand? Okay.
Yeah.
Well, there they want you to use a gust factor of 2.0 because it's very likely that these things are going to be open during a storm.
Yeah.
Okay. So the thing is that it's unfortunate because like you have to, like, one thing I've come to appreciate is that like wind, how it kind of like works, you know, like because I've had a little bit more, let's say, physics. Okay. And I even understand the concept of the vertices that occur, okay, as you know, like you understand a vortex, you know, like a little tornado, okay.
Yeah.
And what happens is that when the wind blows around the building here, it's these little vertices that increase the pressures at the edge of the building, okay. And people like, and you know, when you start looking at this, you start realizing how wind works and all that, okay. Of course, I don't want to get in too much into it, but what I want you guys to ever, like, if ever you're outside on a windy day, okay, if for example, if you're standing outside, like let's say the wind is blowing here, okay, the wind is blowing here, and you're standing on the leeward side of the building here, okay, you're standing here. I want you to be sensitive and see if you feel a pressure on your back as you're standing here, as the wind is pushing this way. And you ask yourself, how's that possible? In other words, isn't the building blocking the wind so I don't feel any pressure here? It's actually the suction that the wind is creating on your body that you feel a pressure on the back of your back of you.
Yeah, I remember that from structural analysis.
Okay, and if you're standing this way, you'll feel it in your face. You know, I find that amazing. You understand? Like I'm out there and I kind of like try to relate what's happening to me with, you know, like from what I learned theoretically, and I try to, you know, and try to feel it physically so that I can get a better appreciation of what they're trying to explain to me about wind and stuff, you know. So now you understand why the internal and external ones are positive here and negative here because of the way the wind will travel through the building. Okay. I'm glad you asked. So that should, okay. Now, guys, like I said, it's not, I know like it's not that complicated. I mean, I gave you most of the values. Oh, one last thing. Where are we at? Can I close this for now, or you guys still have any questions regarding this lab? I think, yeah, that was it. Is that
Yeah, I have a quick question.
on the slab, on a slide, on a particular slide before I close it?
No, I calculated it. Like I found the
Okay, so
total
let's
on
go
the
back.
leeward side.
Let's go back. Now that, okay, you calculated what? You calculated, which one did you calculate?
I calculated both the external pressures and the internal pressures.
Okay, so let's start with this one. What did you get for here? Let's take your values.
That one is what side? That's the windward side, right?
Yeah, exactly. Look, here's the direction of the wind.
Okay. So I had to make sure. If this makes sense, I got 0.612 kPa.
I got the same thing, sir.
0.61. Is that what you got? Okay, you got 612. I'm glad you, 2 decimal places.
Yeah, 6.1.
Okay. That's what you got here. Positive. Okay, and what did you get here on the leeward side for the external? Because that's what you have to do.
I got negative
Well,
7.
no, you don't give me negative. The direction's
0.
already there. So don't give me negative. Give me I already show you the direction, so that already tells you that it's negative. So what's the value you have there?
0.72.
0.72, and that makes sense because here we had a value of 1.7, here we had a value of 2, so this one should be slightly higher. Now, what did you get here for the internal one?
That one I got negative 0.324.
0.324. And what did you get here?
There I got 0.216.
Okay. Now, when you added these two together, what did you get here? Or when you subtracted them, what did you get here?
0.936.
And here you got what?
I got the same value.
You got the same value. So what does that tell you?
Well, they're both the same. The W is going to be 0.936 or
okay.
9.4.
Okay. Or you're going to use 0. So in other words, your W now is going to be equal to 0.94 kPa. Okay. There you go.
Okay.
Now, what happens if this happened to be 1.01 and this happened to be 0.92? What would you do?
We use the 1.0.
Exactly. And you don't care negative or positive. It's the higher, the one that's bending it. It doesn't matter whether, because the wind can be blowing the other way. You understand? So now you got a W of 0.92, right? So
yeah.
So let's take that value and let's go back to. Let's go here. Okay. So here. Okay. So for case number 3. For this one here, I have a WF is equal to 0.94 kilonewtons per meter squared times what?
It's going to be times our tributary area, right?
No, I want to know what a WF is. A WF is not a tributary. It's a distributed load.
Oh, sorry.
Because the tables gives me a WR value. I need to know compared to a WF value.
Is it going to be the spacing between the...
Exactly. It's going to be the spacing of the studs, 0.6. And then, of course, what is the load factor for case number 3? 0.4. This is your load factor. That's for case number 3. Now, for case number 4, you take exactly the same thing here, but you multiply by 1.4, and that gives you the WF for case number 4. And the difference is that here you take these are the same for case 3 and case 4, and here you take 1.5, the value we had on the other table on the first page, and in this case, so your PF here is going to be this. This is your PF value here, but it's already in kilonewtons, and then don't forget that you take this plus this for your PF value for case number 4. And then you go to the tables and you just check PF WR if it's greater than your PR W and then a WR value. See if it's greater than your PF and your WF value, and you confirm whether a 2x6 is good enough. So you're on the right track. Because this is your wind load, you understand? And then your wind load now is in kPa. And the tables give you a WR value, which is in pounds or kilonewtons per meter. And therefore, you have to convert your wind load into a WF value. And how do you do that? You multiply by the tributary width that each stud carries. So you're on the right track. How did that sound?
Sir?
Yes.
Do we check for shear or deflection in this?
Yeah, you check for shear. In other words, you take, for shear, you take the WF from this value here.
Yeah.
That's what you do for shear. And which one, for deflection, what you do is you take, what do you do?
Well, isn't it L over 360?
Yeah, I understand, but what do you take for a W?
The W,
If you want,
the case 3.
No. Yeah, well, you take. I'm sorry. Yeah, you take you know. First of all, you don't take the case 3 for your deflection. You take case number 4 because it's higher than case 3.
Oh, okay.
That's number 1. Number 2, okay. Remember, for wind, the importance factor is 0.75 instead of 1. So what do you do to your W? Your equations for pressure.
Factored, right?
Pardon?
It shouldn't be factored. Like I'm gonna take the value of the W without any.
Well, here the W here that we calculated right now, we said it was 0.94. I'm not saying that that's right or that's wrong, but that's the value that we're using. Okay, 0.94 kPa. That's our wind load right now, right? For strength, for ultimate limit states. What would it be for serviceability limit states?
It's gonna be the same, isn't it?
No, because the importance factor for wind is 0.75. It's not 1.0. So what can you do to this value here?
Multiplied by
0.75, and that will give you the wind serviceability load. Because that's the only variable that changes in all the equations. Everything else stays the same. So you can take that value, multiply by 0.75, and you get the value for S in sand. So for wind, it would be 0.94 times 0.75. I should turn my 0.94 times 0.75. So I would use 0.71 kPa for serviceability. You see? And that's why I show you this table here. You understand? I show you this table here so that you guys can relate to what we're talking about. Okay, that's why here I say that you calculate all your loads for your strength based on 1. What can you do for serviceability? So if these equations, the only thing that changes for serviceability is my IW, then I could take the values I calculated for my strength and multiply by 0.75, because here I use a value of 1, and I get the pressure for serviceability. And, you know, that's how, you know. And there you go. So you would use 0.71 kPa, or you understand, for your serviceability.
So I have a quick question.
Yes.
So for serviceability, we have to recalculate all what we just did, but instead of using 1,
you don't have to. That's what I'm saying. You're using 1, and then you know that mathematically for serviceability, your importance factor is 0.75. So you take your strength and you multiply by 0.75.
Oh, okay, I get it now. Thank you.
It's just math. I mean, guys, like, you know, if all my variables are the same and only 1 changes, I can easily manipulate the value of that by changing the, like, so even if I was doing, even if my, for example, if I did all my calculation based on a high category, okay, I did all my wind for my high category ended up being 1.30 kPa. Let's say that's what I ended up getting for my strength, right? Would I recalculate for the serviceability? No, I would take 1.30, multiply it by 0.75, and then divide it by 1.15, and that's what I would use for my serviceability. I would just be mathematically removing the 1.75 from all my calculations and replacing it with 0.75. That's what I'm doing mathematically. Guys, the more you know your math, the easier your life's going to be. That's all I can tell you. Does everybody understand what I just did here? Or does nobody understand it? Or does anybody understand it? You know?
I understand. So we're just gonna. We don't have to do it.
No, because
we do that math one time
you did this, and here you don't even have to do any prorating because it's 1. So therefore, you take your value and you multiply by 0.75, and it's going to give it to you for serviceability. You understand? Because if you look at your equation, P is equal to I, W, Q, CE, CP, CG. All of this stays the same. The only thing that changes is this one. So I'm just going to change these two numbers and get one for strength and one for serviceability. You understand? Okay, so is it a little clearer now than it was a little bit before? I suggest, guys.
That's clear.
Okay, I suggest you first do the assignment to get into the practice of how to solve, you know, like the problem for strength and serviceability. And then once you've done the assignment and it pretty well corresponds to what we did to the lecture, or take the example we did in the lecture. Of course, I'm going to be sending you the lecture, or, you know, you can look at the video. Take that and follow that, and then solve your problem for your project. But I strongly suggest you first do your assignment, get into the hang of what you're doing, and then after that, take that information and apply it to your project. And that's what the project is for, so that you can see it more into practical terms of how we actually get, where do we get our values in reality? In other words, I don't get a wind pressure out of a textbook. I've got to find one, and I'm showing you how you find that value. You understand? And how you apply it to your problem. You know. Okay, so is there any more questions on these slides here before I exit? And the thing, guys, like, you know, I went through this, you know, like, and sorry. I went through this so that you guys have a very, you know, structured way of, you know, following what I did, so that you guys, I'm literally holding you by the hand, understand? So now you're going to go through it again. And if you really want to understand it, you should go through the whole video and go and review it and understand. And, you know, and then if there's something that clicks, that says, hey, this I really don't get, just ask me, you know, and ask me, and well, I'll explain it to you. So that this way you'll get rid of that little glitch that you might have, and you'll have a better understanding of what you're doing. So it's, guys, I want you guys to get a understanding of what you're doing, because as far as I'm concerned, that's, to me, is more important than just crunching numbers and coming up with a number. Because if you don't even know what numbers you're putting in, you can crunch all you want. It's just going to come out because you might be lucky, not because you understand what the outcome is. I want you to have a little bit of an understanding of what we're doing. So, okay, so on this note, this one we can stop sharing. Well, I'm going to stop sharing. I'm going to close the, well, I can close the PowerPoint. Now, you guys, you want me to open up my ADA? Is that what you want me to do? Or are you guys going to open up your ADA so we can look at it if you have questions regarding the trust?
Sir?
Yes.
I have a question with my trust analysis. I did it, and my results are slightly off than yours.
Well, it could be you're right and I'm wrong. So don't take mine to be like you guys assume that I'm perfect. You know, look how many typos I do in my presentation. So like I could be making mistakes too. So I expect between 30 of us doing the same thing, we can find out who's right, and the other one should be thankful that we were able to correct it. You understand? So if you want to share your like,
yeah, I can share mine. Show what I did.
Okay, show me what you did, and we'll see if you know, if it's exactly like where I might have made a mistake. You know, so don't.
I'm going to allow me to share.
Like when you're saying that you got the same results or very close to it, how far off are you? Are we talking
one unit off? For yours you get 7.2. I'm getting 6.07 for the axial load on the truss.
For the axial load? Okay, show me what you have, and we'll go through it. And
yeah, you just have to enable me to share because I can't.
Oh yeah,
share.
I'm sorry. I usually do that at the very beginning. I'm sorry about that, Anton. Sorry, because I.
There you go. Thank you. Okay. Share. All right. So here. Way.
Yes, I got exactly like you.
Yeah.
Anton.
Yeah. So this is if I go and do view options. Yes, I'm on FX. I just move this for a moment. I get 6.07. But the funny thing is, I redid the whole thing again, and I get a whole different result. I redid it. I'll open this file right now.
Oh, you're doing okay. So you're doing a couple of
I'm trying because and then here, for some reason here, my result is completely different. Just analyze it.
Okay.
And here I get 5.51. I don't understand why.
Wow, Anton, wow.
Yeah, it's really strange.
So you're saying that in one case you get, like, you're talking about the axial force in the web member, right?
Yeah, exactly. So if I click on this, NZ, or that.
Yeah.
Where is it?
It's over. Go over. You gotta go over. It's you're almost there. Sorry.
Wait, 1 second. Let me. I don't know why I can't see anymore. Usually it's like over here.
There it is.
That's VX. I need NZ.
Yeah, keep going. Keep going over.
It's not here. I don't know where it's at.
What happened to your NZ value?
I don't know.
Okay, well.
Find maybe. NZ. Oh.
No, forget about that.
That's weird.
Okay, so Anton, what you're saying is that your values in one case are different from another case. What have you done differently here?
I checked. I thought it was a mistake in the end conditions, but it's not. It's the exact same end conditions. I did exactly how you showed it on the
Well,
video.
I mean, like we can like I said, we can definitely look at the as far as the lengths go. Do you have exactly the same length on both models?
Yeah, pretty sure.
No, I'm just saying, like
I'm pretty sure. Let me just open this one. This is my second attempt, and this is the first attempt. Yeah, the lengths should be pretty much the same.
So here you're getting, okay, so now the thing is, can I see your loads?
Sure, right here.
Can I see your loads? Like,
SID?
No. Go show.
Okay. This. I mean this.
All loads. Put all the loads on at the same time.
All right.
All loads. Okay. So here, for some reason, you don't have a load on this member here.
Where?
Right here. Okay. So that could be something that's affecting your results. You see right here, you don't have a load on your bottom chord.
Bottom chord on the left or right?
In the middle. I don't see any load. I don't see a distributed load on the bottom chord.
Well, here it's. If I look here, it's. Here's 0.1. Oh, okay. That could be a reason. Okay. All right. Okay. So let's fix this.
See, like guys, what I'm saying is that like if we want to get the same results, we have to have exactly the same loading, you have to have exactly the same member lengths, and we have to have, you know what I mean? And okay, so that right there is going to start changing things. In other words, you're putting more load on the bottom cord, you're going to have a higher axial force in your web member. So it's going to get closer to the other one. You understand? If you rerun your analysis now, okay. But I mean, like, guys, what you have to do is, what you have to keep in mind is that, okay, now.
There you go. Now I got it. Now I got what I got in the other one.
Wow.
6.7.
Isn't that amazing? Why?
Yeah, I know, right?
Why?
Actually, the load was wrong.
Exactly. Like, you know, like, so guys, if we have now here, can I ask you a question?
Mm-hmm.
Okay. Can I ask you a question? So far, look, guys, if this is the order of magnitude that you have for the axial force here, okay, this is your TF force, right? This is your TF for this one, okay. And if you go into the table and you look at a 2x4, the TR value of a 2x4, and you multiply by 1.1 because you have a case one system, I think you end up something like 25 kilonewtons, your TR value. So whether this is 6.4 or 5.3 or 8.2, is it going to make a difference?
Not that much.
It doesn't, because your TR value is way over your TF value. So you understand? It doesn't make much of a difference. So what you have to keep in mind is that, you know, like, if you guys think that you need to get exactly the same results that I do, I mean, I try to be precise, but I also look at MR is 10, MF is 7. Wow. So even if my analysis is slightly off, I know I have a lot of resistance that if I've underestimated something, I have some margin there before I get to my MF getting close to my MR. That's what I want you guys to appreciate. Understand? Not that the analysis has to be bang on. The closer your analysis is, the better it is. This way, you can rely on it to do, you know, anything else you want to do with it. But keep in mind what's important here is that you know where I start to panic, or not panic, where I double check my analysis when my MR is almost the same as my MF.
Okay.
Does that make sense?
Yes, sir.
Why do I double check then? Because I better make sure my analysis is correct, because I got no margin. You follow?
Yes, sir.
But if all of a sudden I go pick a member and I get an MR of 22 and I have an MF of 16, am I really concerned? In other words, I could be off by you know, almost 2 before I run into problems. So that's what I want you guys to okay. So here now, all of a sudden you got the same answer back because what? You did the same loading on the member.
Yeah, exactly. That's okay.
There you go.
All right, thanks, sir.
Okay, but what I want you to understand here, can I so that you guys, I will annotate. Okay.
Yeah,
so
sure.
now, okay. So look, can I? Okay, so Anton, this looks very messy. Personally, I can read this very well. I know, to me, this makes a lot of sense what I'm looking at. You understand?
But want to make it bigger or?
No. Leave it the way it is, because I know, and for people that are looking at this, they don't even know what the hell they're looking at. You follow what I'm saying? Okay. But so what I want to do is I want people now. What I want you to do is on top of this. Okay, go to the. Okay, I'm gonna ask to share. Okay, I'm gonna ask for request remote control. Okay. Now on top of this, I see, like, you guys, like, to me, I like to work with tables. Okay, and this to me is very messy, but I'm so used to these analysis program. I've been using analysis programs since 1978, guys. Okay, they weren't as, you know, and so when I look at this stuff, I know what they're trying to show graphically, but what you have to understand is that what they're trying to show you graphically, what it really means analytically. That's what you have to get from this. Okay. Now, can I annotate? I just want to annotate.
Yeah, I approve.
Annotate. Okay, there we go. Okay. So now what I want you to do, Anton, also at the same time, I want you to put the moment results on this.
Moment. Okay. Sure. It's right here.
Now I want you guys to all listen to this. Okay. Put the moments at the same time. MX. Okay. Now, Anton, can you do me a favor? Go to your units and change your units to imperial. Because you're like, no, you got to go to, don't change them there. Go and change the close.
In file.
In the preferences. Go to file, preferences, and put
imperial. You want it to?
No, I want a metric. I want the solution in metric because we're doing everything in kilonewton meter. I don't want everybody to. Okay. I know why you did it in imperial, because you wanted to know what a 2x4 was, right?
Yes. Yeah.
I know, but okay. So there you go. So guys, everything is, see. So now we have NZ, and we have MX. Okay. So basically, what we're saying here is that let's start with the most simplest one. Okay. Here you see that it's drawn like this. It's drawn like this. The reason why it's drawn like this is because it's positive, and this program says that when you have a positive axial force, you have tension. That's what the program is telling you. That's what the graphic is doing, okay? So they decided that positive was tension, and therefore, if this member ended up having an axial tensile force, they would show it above the member. That's how they're drawing it. Now, what's important for you is that here you see a positive value. So now that's where they draw it above the member. So here, for this member here, the TF value for that member there is equal to 6.07 kilonewton. Now, all you got to do is go in the tables, look for a 2x4, and look at the TR value of a 2x4, multiply by 1.1 because you have a case 1 system. And if it's greater than your TF value, you can put a 2x4 there. Okay. Now, that's this member here. Now, this member here is drawn below. So that means it's in compression. So here I have a CF value. CF is equal to, and here's the number, 5.57, 5.57. Okay, so that's your CF value. Now you got to, I'm sorry, I shouldn't say CF because I'm talking about steel here. Where's my eraser? I'm going to talk in wood. Sorry. Okay, this is my PF value. Now, how do I calculate my PR value? Well, unfortunately, I can't use the tables here. So what I got to do is I'm going to start with a 2x4. Okay, I'm going to assume I'm using 2x4, and I have to use the value phi f c a k z. I have to use a formula and calculate what, and then how do I get the length of my member? Well, you just ask ADA to give you what the length is here. There's the length, and that gives you your LB, and that gives you your LD. They're both the same because they're not laterally supported in any way. And then you calculate, and if this happens to be greater than this, you're good. So that now you've taken care of this, and you've taken care of this. Now, which one do you want to do? The compression or the tension combined one? Well, let's do the top chord. So now I look at the top chord. I have a bending moment here. This is my MF value. So right here I have 1.13. And I look for the highest CF value right at that point there. I can't really read it. It's really messy, but I think it will be 17.16. Am I correct, Anton?
Yes, sir.
So my MF value here is 1.13, and my CF value is 17.16. This is kilonewton meter, and this is kilonewton. So now I do MF over MR. I'm sorry, PF over PR, and then I check to make sure for a 2x6 that the ratio is less than 1, and then I know that I'm good for the top chord. The bottom chord, well, I'm looking at here. Here's the highest tension, which is 16.97 right here. So therefore, my TF value is 16.97. And my MF value, I can't really read it because it's so goddamn messy in there. So I would have to go to the table, and I would get my MF value, and then I put TF over TR plus MF over MR. Is that less than 1? Then I know I can use a 2x4 there. And that's what you get from So all those values you get in the examples that I throw at you in a textbook, this is where they come from. In other words, where do they get the TF values? Where do they get the CF values? This is the analysis. This is where it all comes from. And in reality, so like you're saying that my values aren't the same as your values, or like your how slightly? Can you do something, Anton? Let me get clear this, okay?
The moment on the bottom chord is different by quite a bit.
Yeah, yours and mine.
Yeah. So if I on like on the first number, it's 0.09, and then like at the bottom of the two webs, it's minus 0.3.
So Alec, you're saying yours is different from his.
Yeah, and it's different from what you had.
Okay, so one of us is more accurate than the other one. Is that what you're saying?
I don't know if it's more accurate, but they're definitely different.
Okay, so hold on a second.
I mean, if you want, Alex can share his.
Yeah, like Alex, can you put yours up?
Yeah,
I'll put mine up. Okay, let's go to yours. I love this. This to me is great. You know, I love looking at different and trying to find where I might have gone wrong. Where you know, this is great. You know.
Okay, do you see this?
Okay, this is what I showed. This was my results, right?
Yeah, exactly.
They're close to. Okay, and what did you get, Alex?
So let me just go to the moment.
Yeah, just put the moments. Forget about the axial force because everybody gets confused. Okay. So you got 0.17, and I got 0.11. Is that it?
0.3.
I got 0.3.
And then here, 0.16, and it's 0.09.
Yes, sir. I got closer to you.
Who? Adriana, you're closer to my answer? Yeah.
Your answer was 0.30, right?
Yeah, 0.3
about.
about.
I have 0.25.
Yeah, me too.
0.25. Okay, so like we can look at, okay, so let's see. Let's see what the, so Alex, did you add the self-weight of the truss in your analysis?
Yeah, I believe so.
Let's go take a look at that. No, you got to go to load combination. Let's go load combinations. Load combinations. Yeah, that's good. Go to the next one. Ultimate 1.25 your dead load. 1. Yeah, you got them all in there. And okay, so that's good. So that at least we know that's good. Now let's look at your. Let's just start with your snow loads. Okay, just do one at a time. Yeah, your snow loads are perfect, right? Because that's what it's supposed to be, right? 2.5 times 0.6, that gives you 1.5. Yeah, that's perfect. So take off your snow loads. Let's go to your superimposed dead loads. Did I use 18? Your bottom ones seem to be higher than the top ones. Is that the way it's supposed to be?
I believe so, yeah.
I don't remember because.
Here, let me check.
I don't remember.
0.12 and then 0.18.
Okay, so we're using the same loads, right?
Yeah.
So we're using the same loads, and we're using exactly the same loads. So your loads and our loads are exactly the same. We're using and your member lengths. I didn't show my member lengths, right? Are we using exactly the same?
I don't think so.
Sorry.
No, you didn't show up. But I what I did was I went into the trust. Like where was it? This guy.
Sir.
I put
sorry, but I noticed something.
Well, what you have to do is you have to go to structures, Alex. Go to structures here, okay, and go. Oh, first of all, you have to get on structures. Yeah. Go to nodes. We'd have to compare our nodes to see if we have exactly the same. You understand? The same geometry.
Yeah.
That's
sir.
Yes.
Sorry to interrupt, but I think from what I see in the drawing, there's no pin connection in the middle. Like, I don't know if that changes anything.
Yeah, this is going to change something.
where-
Right here, he has a pin connected. Yeah, this is already one thing that's going to give you a slightly different answer. Here, you made it continuous, Alex.
Here.
Yeah, like let me share.
Okay.
So change that to a pin on one side.
Oh, okay. I think I'm having the same issue as Omar. Okay, so that would be.
Well, you can see which one's your I and your J if you go, anyways. So, because if you know your nodes, you know which one to do it. You understand? Take your time. Don't worry. We got time. You haven't released it yet.
Well, yeah, because if I do that, it goes to this node.
Yes, because if you go to your, because the both members go. I'll correct that for you right now. Okay, close that. Undo what you just did. Okay, go to your structures, or let me share with you if you don't mind. Oh no, go. I'll tell you. Go to structures, Alex. Go to structures. Go to some members.
Members.
You probably have the same. See, you have the same number here. Change the numbers. See, you have 8, 8. Leave one as 8, but make the other one like 9 or something. And then here you have 7. Like these, this doesn't work. You can't have the same numbers. You understand?
Okay, so that should work. Well,
no. Sorry, no, not that. I'm sorry. Like, hold on. No, that's not it. No, no. Cancel. Don't change anything. Cancel. Don't say okay. Cancel. I thought okay. So you have member 12. So how come you can't change the end condition of this member? Why does it go here right away?
Maybe if I try this one. No.
Sir, I also had the same problem. It was because of my nodes.
It's your nodes. Your nodes aren't correct. Yeah. There's something wrong with your nodes. That's what it is.
Like what I did, I added another number.
That's right. You have to change the number. You have to change the number. Oh, here it is, 8, 8. So this one has to get changed. Put this one. You know, you see where the one of them has to change. 10. Okay, try that. And now you can change it. Okay, now rerun your analysis. It's going to make a big difference in the continuity. That continuity makes a big difference in your analysis. Okay.
Yeah, I see. Okay.
And you should be getting the same answers about saving project. Don't worry. Hey, is Rania still there or is she gone? Rania, she's gone? She's gone for the day, I guess. Yeah, just analyze. Yeah, analyze.
Oh, okay, that's better.
It looks better, okay? So I had 0.3 and you have 0.24. Like Alex, like I said, yeah, go ahead.
I also have the same as Alex, and for me, I did mine 3 times without like looking like I did it 3 times independently, and I still got the same answers.
Okay, guys, look, like I said, I get what? I get 0.3 as opposed to yeah. I don't know. And then here, like for the negative moment, I get 1.11. It could be I used a slightly different height of truss, guys. You understand? Let me. What I should have done is I should have put down all my nodes. So if you guys, because this was crucial, what you put as the height of your truss. You understand?
Well, I believe it rounded it, so I'm not sure.
You rounded it up, right? Or down?
I believe I put 3 digits after the decimal, but it rounded up to like only 1 digit.
Yeah, well, the computer will round it up, but I think it will use the 3 digits in its calculations. But or maybe you did it more accurately than I did it. You understand? But guys, what's important, Alex, is you see, like this is the same order of magnitude. You understand? It's they're both correct. Which one's more correct? Well, if your loads were more accurate than mine, yours might be. You understand, and vice versa. But look, here we have the same axial. You see the axial force here. The moment in this member is the same. And you know, don't you find that interesting, guys?
Are you trying to point? I don't see it.
Okay, sorry. Let me share. This is what I find interesting. This is the stuff that I want you guys to appreciate. Let me just request remote control. Okay.
Okay.
Okay. And when you look, what I like, can you see my pointer now?
No, I don't.
Can you see it
Oh,
now?
now I do. Yeah.
Okay.
Yeah.
Now, what I love about what I love about this program, okay, is that I like to annotate so that this is what I love about this program, is that I'm pinned here, right, and I'm pinned here, right. I got no load on the member, but yet I get a bending moment. That's a small one, but I get a small bending moment. That's how good the program is. It calculates the bending moment under the self weight of the member. Isn't that amazing?
Yeah.
I mean, guys, that to me is like, wow, I know it's like 0.01, it's like peanuts, right? But the fact that the program will actually calculate the bending moment of the self weight of the member here, in other words, multiply the self weight by 1.25 and do the calculations. Don't you find that amazing? You see, look at here. So that means that we basically have the same member here, and we probably have about the same length. You understand? That's what that tells me also. You know. And that here is like, Alex, we've got the same numbers, you know, basically. So I'm not worried about that.
And the axial loads are pretty much the same. It's like
exactly. So your analysis correct and my analysis correct. Like I said, if we wanted to really compare, like to make sure we wanted to get exactly the same results, we have to compare our nodes. That's the only thing that there might be a slight difference. You understand?
Got it.
And maybe I should have, copied my nodes and put them on the spreadsheet so that if we all had the same node, we would all end up with the same result. But I don't want to end up with the same results. You understand, guys? I want to see this variation. I find it more interesting. You follow? It gives us
either way, the resistance of the member, it's going to be greater than whatever we have, correct?
I'm sorry, can you repeat that?
Like the resistance of like a 2x4 or a 2x6, it's going to be greater than what we have on ADA.
If I'm not mistaken, I think I checked this. I think that this one is pretty much at POMAL at when you do the PF over the PR and all that. I think this one is pretty much at its limit. You understand the ratio? You understand?
Okay.
These ones are going to be over designed, and that's why, like in a real truss, guys, in a real truss with the fabricators of these trusses, okay. The only reason I told you to use a 2x4 here because you only have 2x4s in your tables. You understand? That's why I asked you. But in reality, in a real truss, these would be made with 2x3s. You understand? Because and they would be sufficiently strong. The web members are usually made with 2x3s, and they're sufficiently strong to take care of those axial forces. You understand? But since there's no 2x3s in your hand in the tables that I give you, and even in the handbook, I tell you to use a 2x4. But in reality, those would be made with 2x3s, and I wouldn't expect you to calculate a 2x3 from the formulas. I mean, that's pretty redundant. It's not. It defeats the purpose of what I'm trying to teach you. But in reality, 2x3s would probably do the trick for both. So that's good. That's good. I'm happy. I'm happy we're getting slightly different results. It kind of puts me into question what I'm doing. But see, like just this one issue here. I can tell you, I'm sorry. It's too bad that Rania left. Okay. Like what she did is I don't know. She sent me her ADA, right? And she said I'm getting completely different results as you are. Okay. Can you close the Can you close my little sketch? And what happened was she didn't realize that this was still red here in her analysis, and this was still red. And of course, ADA, what that means is that she hadn't released the bending moment, the Z, the MZ here, okay? And of course, if I'm going to fix this, the results are going to be completely different. And that's why you have to be very, very sensitive, okay? When you're analyzing with ADA, okay? If you tell AD that I have fixed, like just to give you an example, Alex, can we just do it for fun? Go back and just change this to fix, and you'll see how the impact it's going to have on the results. Just go and then your supports. Put this back to fixed and fix. Okay. Yeah. Both of them. Yeah, I want to show you how the big impact that has on the. Okay. Then you can put it back after, right? If you want, you can even just do it on one to show you, but okay. Now you remember slightly the results were, right? Let's clear the drawing so that
It's taking a lot longer than usual.
Yeah, it's kind of. But you're using the you're using whatchamacallit, you're using the
VMware.
Yeah, right.
Yeah.
See, mine is a little faster because I have it right on my computer. You understand, Alex?
Yeah, I had it on my old computer, but
I
had to
understand.
wipe
Don't
it,
worry
so
about it.
I'm using VMware.
You know that you guys can just send an email to GreatTech, say you're a student, and they'll give you a 1-year license. Huh?
Yeah, I should. This is just a lot easier though.
What? Oh yeah, of course. I'm just saying, like, it's nice to have it. But look at the difference now in the bending moment.
Oh yeah, here.
Right there, and look at even the one that right here. Like, sorry, am I? Look at this one. Remember, this was 1.11.
Yeah.
Look, and if you go look at the axial forces, just for the hell of it. Yeah. It's even reduced. You understand? Like it changed the act. So just this one, one little support that was, and then the thing is that it helps you to, to redistribute a lot of your moments and stuff. But like how do you actually create a fixed support on a wooden truss? Because if you analyze like this, that means you'd have to find a way to fix the truss to the wall and make sure that they act together as one. How do you do that in wood?
Weld it.
Yeah, well, I tried welding wood once, but it burnt on me, so that didn't work very
What
well.
about glue? Does that work?
Pardon?
Glue, like an adhesive?
I think the only thing that you can actually do here, what you would have to do is you have to sort of like, you have to make steel HSSs, right? That you can fit your wood in, and you'd have to, like, in other words, you'd have to make like a steel joint like this, out of steel, and make sure that it's strong enough, and then you'd have to slip your wood inside your steel, and then the steel would actually do, and make sure that this is long enough so that it can develop that bending moment. You understand? And that's the only way I can see it, that you can actually fix wood. You understand? So you have like a steel joint that you slip your wood inside, and it's the steel that actually fixes the wood at the joint.
Got it.
You see? That's how I see it. But is it worth it? No. No, it's not worth it. Hey guys, I'm proud of you guys. Nice job on the truss analysis, but very nice, very nice. Oh, Alex, don't forget to remove those fixity.
Yeah, for sure.
Okay.
All right, thank you.
Nice job, guys. Nice job.
Sir?
Yes, go ahead.
So I have a question because, yeah, I have the same as Alex. Maybe when he checks his deflection, do we use the deflection in the strong axis or axial deflection?
You're always checking the deflection in the strong axis.
Because apparently when I checked it, it doesn't work. Like the one in ADA is much higher than L over 360.
You sure?
For almost all of them. Yeah, for the top chord, bottom chord, and...
Oh, no. Like what you have to do is this. Look, when you're checking deflection, okay, I'm glad you asked the question. Alex, did you check your deflection?
Yeah, well, no, actually, I didn't.
Okay, so you said if you guys are all getting the same values approximately as Alex as mine, okay? So rerun your analysis.
Yeah, I'm doing that right now.
Do that right now, okay? And I'm gonna ask you one little thing, okay? Okay. Okay, rerun the analysis. Okay. Now I want you to I don't want the I want for service. Go back. Just go back. Put serviceability. Okay. I don't even want to see that. What I want to do is you have serviceability here, right?
Yeah.
I want you to click on this on the node here. Okay. So in other words, this is just your snow load, right? Right now?
Yeah.
Okay, so click on the node and go click on this node right here. Double click on it. What's the displacement?
This much.
6.86 millimeters, okay? So if you take this length here, that would be your deflection, you understand?
Okay, got it.
6.86 millimeters would be your deflection over that span. So if you take this as peanuts, and if you like, okay, so close that, press OK, cancel. Go to the, look at results. Look at the results. And go, like, yeah, deflection of the strong axis, apply. There you go. Exactly the same thing. So that's how I would check it. I wouldn't even, you know, I would just go look at the displacement of that joint, and that would give me the deflection.
And that's only because it's at the exact middle, correct?
Exactly. That's I'm taking a shortcut.
Got it. Okay.
So now, who was talking? Justin, were you the one that was talking to me before?
No, it was Jan.
Yeah. Okay, Jan. Jan, very simple. You see that this is your deflection now. Okay. So now if I take, so if I take 27 feet 9 inches, how many meters is that? Because this is your L here. Your L goes from there to there. So what is that in? So 27.75 times 0.3048, or if you would have converted everything to meters. So I have, this is approximately 8.46 meters, okay? So if I multiply this by 1,000, divided by 360, I'm entitled to 23 millimeter deflection for the L over 360. I only have 6, so it's strong enough.
I think that makes sense. Thank you.
And that's what I love about ADA, because like to actually calculate the deflection of this truss manually, it would take you a day. You know. So this was nice about ADA. You get it right away. You know, it does everything for you. So therefore, that's it. So, so and you said you got exactly the same value as Alex here.
Yeah.
Okay, great.
Same as everything.
Great. So there you go. So that's how you check deflection. You just check the displacement of that node, or you can actually do it on the strong axis, as it gives you exactly the same value. You understand? Because this is where your gypsum is going to be installed, right? Right underneath here. Okay. So you want to make sure that it doesn't sag more than 23 millimeters when the snow load goes on the roof, you know? Nice job, guys. I hope you're starting to get a little bit more appreciation of what ADA can do. Yes.
Sorry, I just have a question about the snow load, because I'm doing the calculations for my cases 3 and 4. And the dead and snow load, is it the dead and snow load that you wrote down, like specified dead load, the results from ADA? Or is it the dead and snow load?
It's the specified. So Alex, can we go do something? Sorry, I don't want to say.
Yeah.
Can we do something now? I want you to do one more load combination. Okay, so go to the load combinations. I want you to do one more load combination. This is for the exterior wall. I want you to know, okay, call it ultimate, one more load combination. I want you to call it like specified dead load. Okay, so call it dead load or specified dead load, whatever, you know, specified dead load. Okay, that's it. Press OK, and I'll go to load. Press load
factors.
Load factors. Now click on that. Now click twice. Bring up dead load on the first one, and superimpose dead load on the second one. And those are your dead loads. Okay, so press OK.
1-1.
1-1, yeah, because you want them to be specified. You understand? You don't want a load factor. Now rerun the analysis. You have to rerun the analysis. Take the time. Just want to show you how I got. Okay. So let it. Don't worry about it. We got time. So rerun the analysis. So Adriano, this, you see what we're doing? Okay. Yeah. Now, okay. Now just go to the results. You go to the results here. Go to your results, and you just want to see your RY, not your deflection. RY. Okay. Apply. See 1.55. I think that's what I gave you in the lab, right?
Exactly. So that's why I want to make sure.
Now, Alex, go down and do these serviceability limit states. Go change the load, yeah, because that's just your snow load. There, 7.03. You see, so that's where I got it from ADA. And since I knew that my trusses were going to be spaced exactly the same spacing as my studs, this becomes my actual forces.
Yeah, okay, perfect. Yeah, sure. I just want to make sure, that's why.
Okay. Yeah, because you want to use the specified ones, because at one point you have to use only half the snow load. You understand? And then of course, but what I want you to appreciate that this is already an axial force, so you don't have to worry about tributary width, tributary, you know, this is already your axial force. And that's only because your studs are spaced exactly the same spacing as your trusses.
Thank you, sir.
Okay. So what that means is that if, you know, if by chance the truss, if the truss happens to fall exactly in the same location as the stud here, like let's, in other words, here's my truss on the roof, and the stud is right underneath it, well, that's exactly what happens. Now, if it happens to go over, that's why guys, I want you to appreciate one thing. Why do we double the plates on a bearing wall? Is because sometimes the member doesn't fall exactly over the stud below it, and this acts like a little built-up beam to help transfer the load to each member. You understand? So, okay, so there you go. So we have exactly the same values. Okay, so like Alex, if there's a slight difference, it could be when you gave the height of your truss, you could have been more precise than I was. You understand?
Got it.
As a matter of fact, I am curious. Now you got my curiosity. You got 5 more minutes. We'll call it a day in 4 minutes. But no,
Do you want to see the node?
Yeah, I want to see your nodes because I want to see if structures. Yeah, first of all, you have to be on structures. Yeah, structures node. Just your highest node. What do you have? Y. The highest Y. It's in meters, right? So you got 2.11 meters.
Yeah.
Okay. So because what you're supposed to have is like 27.
Do you want me to change it to imperial?
No, it's okay. I can. I've been converting all my life, Alex. Don't worry about it. Okay. Divided by 4 equals times 0.3048. Yeah, that's what it's supposed to be. 2.114, right? Yeah, that's exactly what it's supposed to be. Oh, I mean 2.11. The computer rounded off. I'm pretty sure you put it to 3 decimal places, right?
When I did the height in imperial, yeah.
Yeah, exactly. Anyways, so I'm curious. Well, it looks good. I mean, like I said, I'm sure that there's got to be just a slight difference in our geometry, and that's why we're getting slightly different results, because our loads are exactly the same, our supports are exactly the same, the end conditions of the connectivity exactly the same. So there you go. It's got to be there. Where if you're asking me if I had to concentrate where I can find the discrepancy between your results and mine, I'd probably look at this. This is the first thing I look at. Because I'm pretty sure you put 2x6 and you put 2x4s for everything else, right?
Yeah.
Yeah. So the only place I can see, the only other place I can see there might be a discrepancy is right here in this table. So we would look at our table side by side and see where the variation is, and we'd probably find why we're getting slightly different results. Understand? But like I said, the objective here is not to get the exact results. The objective here is to make sure you're in the right order of magnitude, right?
Yeah.
And if you're in the right order of magnitude, you're on the right track, as far as I'm concerned. You know. So doing a good job, guys. Good job. Okay. Well, if there's no more questions, I'd like to call it a day.
I have a question.
Go ahead.
When I'm choosing my material, which one do I choose actually for my?
Well, you're gonna have to. I'll show you if Alex can show me. Go to pick a member, Alex, any member, just to show him what we did. When you go to materials, this is the one 1AV SPF 12 right there, and show him where that material is. No, he doesn't want. You know?
Yeah, material.
Okay, you go to wood. You got to go to wood, timber, visual, SPF. It's the second one because that's visual. And the SPF, that means grade number 1 and 2. This is select structural, the first one, and the third one is grade number 3. Okay.
Perfect. Thank you, sir.
There you go. There's your material. But the material would not have a bearing on your analysis. Trust me. Oh, it might have a bearing. Yes, because I'm pretty sure they put the density of that wood. Yeah, so it would have a bearing on your analysis in this case. Yes. Because different species have different densities, so it would have a slight impact on your analysis, but that's about it. Okay. because if you guys want to convince yourself that when it comes to structural steel, since the structural steel has the same densities, whether you're using the American one, the Canadian ones, you can run the analysis with Canadian steel, run the analysis with American steel, and you'll get exactly the same results. The only time it differs if you ask the program to calculate the stresses, but not the forces. Understand? Okay, so there you go. Nice, 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 nice. So you're up to speed, Alex, on everything, right?
Not my drawings. I still
No,
have to
no,
do a
no.
bit
But
more on that.
did you check? Did you check all the resistance for each member yet, or like in other words, did you check the TR value of the web member, the CF value of the web member?
Oh no, I didn't do that yet.
Okay, so that you haven't done yet. Okay, so you're just about a week behind. That's it. Okay. Okay. Well, great, great. Looks good. Looks very good. Okay. I hope you're enjoying it. That's what counts.
Yeah, it's fun doing ADA models.
Well, I mean, it's fun to understand what the model is doing for you. That to me is more important. You understand?
Yeah.
No, doing a model and then not and seeing a whole bunch of numbers, not being able to relate to it, is pretty, you know, it's pretty insignificant as far as I'm concerned.
It's interesting to see like how the errors affect like what exactly.
Oh, yeah, and what I like about ADA is that you can tweak. And it's, you know, I want to change this. Am I going to get a better result? That's what I like about ADA. What
And
about
it's
if I
quick.
do this?
It doesn't take forever to do all the hand
Exactly,
calculations.
exactly. So you can tweak and you can play around with it and you can start optimizing. And what about if we do this? What about if we do that? You know, and then,
Yeah.
you know, and of course, ideally, like you save the file that you want to keep and you run you're tweaking in another file, you save as, you know, and I call it, what I tend to do is I call it tweak number 1, tweak number 2, you know, so this way I don't have to go back and change it, right? And then if I see that I'm getting something better, well, I keep going. If not, well, I go back to my original thoughts, you know. But it is fun. I mean, to me, like you guys never had the hardship of doing everything manually. So you really don't have a good appreciation of what this software is doing for you. In our days, for example, we had to do all of this manually and it took forever, you understand? Forever. And even at that, certain things were almost impossible and we only had these approximate methods. So we only got approximate values, but they were good enough for design. You understand? And that's what I'll keep making you guys understand, is that the analysis here is more accurate. That means you can be a little bit more confident that that's what how it should react or should behave, and give you a little bit more confidence in doing your design. But what I found fascinating about this is the time it saved me from when I used to do it manually. Wow. And then, like, you know, it's like the number of iterations I can do over and over again that before I would never even contemplate. So before it was like you do it once, you get it right, you don't do it again. You just keep going with that, you know. Whereas with this, you can do it over and over and over, and it's so much fun. You know? So on that note, I hope you guys are all ready for steel, or hope you'll be ready for steel. You shouldn't panic. You should do okay in steel. So no worries.
Sir, for steel, we don't have any assignment, right? Like that you gave, or
no,
another
not
step
on
to
tension,
do?
not on tension members. Like you'll have, because
And
like
also for the project step, there's no.
Like no. What's going to happen is that because this is just to get you to, you know, start visualizing how tension members behave. Okay, and then we're going to take that and we're going to apply it to a real joint where we're going to be putting the bolts and then checking all those failure planes for a real connection. You understand?
Yeah.
So like baby steps. Because if I would have thrown that, you know, if I throw that at you all at once, everybody would be discouraged, right? So this way, we take it and we'll move along, and we will, you know, because as soon as you understand one thing, then it's easier to move on to the other thing, so that you see the relationship. Understand? And that's just like, for example, I'm pretty sure that your understanding of bending moment diagrams now are a little bit stronger than they were when you were doing physics. I hope they are. You understand? And so on. You see. So and that's like anything. Like slowly, as you use more, as you use this stuff over and over again, you start seeing it in its right perspective, and you get a better understanding of what you're doing with it. You know. And it's always when you get those aha moments that you realize that now it all falls into place. And that will happen, guys. It takes time, but it will happen if you keep working at it. So do you remember when you did math the first time in your life and you were all lost? And now when you look back at some of the things that you were looking at, you said, why was I so lost? Do you guys
I still feel lost.
It depends on the level of the math, I hope.
Exactly. Yeah.
You know, I hope you don't feel lost when I say 1 + 1 = 2.
Oh, no.
There you go. You see how you mastered that? There you go. You master that one. So all of a sudden, if I tell you that 1 + 1 = 2, you and I won't even have an argument. We both agree. See? I understand as it becomes more abstract, it becomes a little harder, but don't worry about that, you know. But at least a lot of it, you feel comfortable with it, right?
Yeah.
I hope so. I mean, but the first time you go around, I mean, like, so it's like anything, guys. It does come. It does come. Like sometimes a little bit faster and a little bit slower, but just don't get discouraged. If it's important to your career, if it's important to what you need to know, it will click one day. So, and that's all you have to worry about. And if it never clicks, well, maybe you chose the wrong career. I'm sorry to say, you know what I'm saying? But eventually it will click and it all starts putting together. It's easy for me, right? After 40 years of doing it.
Yep.
I mean, it helps. It helps to see it. I'm sure your capacities of reading drawings in your third year are a little bit stronger than they were in your first year, right?
Yeah.
And I'm pretty sure they're not half as strong as mine are. You follow? Yeah. But eventually you will be reading drawings as well as I do. You understand? We all understand. So that will come with time, guys.
For sure. It's all practice and experience, and
it's always like exactly by seeing it over and over again. It's like playing an instrument, right? The first time you play the instrument, it's noise, and then as you play that instrument over and over again, you start getting nice music, and then eventually you start developing your own music, and that's what happens. And that's
you start enjoying it a lot more.
Because it gets a little bit easier and it's a little bit more pleasant, and you see the results a little bit faster. It's beautiful, you understand? And guys, you know, like I said, 40 years. It's almost twice your age right now. So, you know, so be patient. It's gonna get there. You'll get there. You know, that's all I gotta say. Okay. So in the meantime, if there's anything, guys, feel free to ask me. I'm more than happy to answer your Mayos, and if I can't, I will definitely schedule a meeting, and then I will definitely send you the video and the lecture of today, so you guys can have that in your file. And in the meantime, stay safe, and hopefully we'll all be here Monday morning to do the test. Sounds good?
Sounds good.
And on that note, guys, take care. Talk to you next week.
Bye.
Thank you, sir.
Bye-bye, guys.
Thank you.
You're welcome. Bye-bye.